So we can start. Welcome everybody to YAGN. My name is Pedro Capello. I'm the organizer of this meeting along with Massimo Dotti, who's sitting here in the second line, and Ciro Pinto, who will give us an introduction in a few minutes on practical information. So just to give you a little bit of history, Massimo and I created this series of events 8 years ago to have a space where postdocs and students could present their work, ask questions, discuss freely in a very informal environment. So this is the reason why we have very long discussion sessions in the afternoons and also very long Q&A sessions at the end of each talk to give you room and space to discuss, ask questions, as many as you like. So all I can say is enjoy the talks, ask as many questions as you can at the end of each talk, if possibly, and most importantly, have fun.
Thank you, Pedro. He was speaking like this because there's a microphone, and this is going to get streamed on the YouTube link. There's also a video, so if you stay close to this, it will help. Devo spegnere questo. Okay. Okay. If you also like this microphone, you can go ahead. Here is also a pointer, so you can help yourself if you need it. Yes, I'm Ciro Pinto. I'm a researcher here at INAF since 4 years. INAF is a great, actually the greatest astrophysics department in Italy with 16 or 17 seats all around Italy. It's like the Italian version of ESA or NASA. Just very quick information. Welcome to the CNR, the National Research Council, or Consiglio Nazionale della Ricerca, which is more general than INAF. It comprises different kinds of scientific topics and is also scattered all around Italy. And they are actually our host here, and they will host also your conference. You managed to get here, so you don't need this kind of information. The only thing I wanted to say is that there are 2 train stops, and they both work with L'Amalfa being the closest one. Between here and San Lorenzo, there is a supermarket, just in case you may need anything. It's called Deco and is really nice. To get around, this is the largest conference room in the building. There are also other ones. For water dispensers, there are just here near the bathroom of the women. No, they are broken? Okay, so otherwise you can use the ones that we have at INAF on the 4th floor, but I would recommend you to ask some colleague of ours. In any case, we're going to have a catering service which will provide also water, so I'm going to actually tell you about in a while. If you want to use Wi-Fi, please use Edram, but you will need to remember your name and your credentials of Edram, name and password. Otherwise, there are a few vouchers here in the front row. Also, take your badge here at the front row, and there is also a printout of the program if you need it, and some informations which I'm actually showing you right now. Please abide the code of conduct, which is really important. Pedro was very kind to make a super clear version on the website, and bottom line is be kind to each other. We don't want any troubles. We just want to have fun. For the program, as I told you, is on the website. Otherwise, there are some printouts here. Please send the slides to YAGN2023 ahead a day in advance, and also to the summary speakers, so that they can provide a very nice summary, including your slides, which is great. Regarding time, please stay within time. The later we get to finish each session, the shorter will be the coffee and the lunch break. So you know what I'm talking about. Everything will be streamed with the exception of the discussion section, because we want to make it more lively between of us. And so just feel free to ask any question. Don't be shy. We're not going to stream also the discussion. If some of you don't want to be streamed while giving a talk, even just a presentation, let us know, and we will tell to the service area. Actually, in the service area, there is Laura, and she's being really good so far. So she's ready to help for anything. Caterings will be offered by Esdra Bar. We are going to have 2 coffee breaks and lunch breaks, as indicated by the program. And I had a look yesterday. It seemed promising. So that's why keep your talk on time. What else? If the weather is decent, especially the wind is not going to be as strong as yesterday, which was blowing quite a lot, we're going to have lunch in the gazebo, which is all around the corner here on the left. If the weather is going to be crap, but I don't think so, we will take food from a small meeting room here in the front right, and then we can hang out in the large room here, and there is also a canteen where you can sit if you prefer, and some sofas. Social event, we wanted to give you a flavor of the typical Palermitan and Sicilian street-like food. And there is this very nice place called Mercato San Lorenzo, or San Lorenzo Market, not far from the metro station. If you can't access Google Map, there is a printout of this here, but it's very simple. You walk straight, then you turn right where there is the supermarket, and you go to the subway San Lorenzo, and then you keep going straight, basically crossing the bridge, and on the roundabout in Viale Strasburg, I think you turn left, and there is after 200 meters, there's an entrance to the market. But we will go together, don't worry, tomorrow afternoon, so you're not gonna get lost. The only thing, bear in mind that the last trains to the central station depart around 11. Staff, so the people having badges with a yellow spot are those who belong to the SOC and will take care of the program and stuff. The people with the blue, with the pink badge, they are the LOC, and they will take care of logistics and similar things. So please ask those people if you need any information. And I think this was the last question. Sorry, the last information. If you have any question, otherwise we will proceed to the first talk. And who's the chair? You are the chair. You are Matteo or Luca? Luca Broggi. So Luca Broggi will be chairing the first session.
So, hi everyone. Before starting, I'd like to understand if all the speakers of the first session are here. So, I see Elisa there. Is Laura Di Gesù here? Okay. Hi. Federica Ricci. Perfect. And Chen Chen Chin. Perfect. So, sorry. So, please welcome Elisa Bortolas from the University of Milano Bicocca, who will talk about the importance of characterizing partial stellar disruption events in the era of LSST. So. Do you prefer this microphone or that one, Elisa? Okay. So please welcome Elisa with an applause.
So thank you so much to Luca and the organizers for giving me this nice opportunity. And well, it's actually a great pleasure for me to open this YAGN meeting. I've been coming to those events for quite a few years now, so I'm very happy to be around for one more year. And today what I'm going to talk about is tidal disruption events, which is something that got my interest in the recent years. And I want to start with a little bit of introduction and motivation of why I believe those sources are very interesting. So first of all, what is a tidal disruption event? Well, this happens when we have a star that comes too close to a massive black hole that typically sits in the nucleus of a galaxy, like our own Milky Way. And the star, when it gets too close, it gets ripped apart by the tidal shear of the massive black hole itself. And as a result, what you get is a very bright electromagnetic flare that can be observed up to cosmological distances, basically. And the cool thing about tidal disruption events is that they fade with a characteristic light curve that makes them easier to recognize. And so we hopefully can tell those are tidal disruption events and have information on, for instance, what is the extract information on the mass of the black hole that destroyed the star, and so on and so forth. And why is this so interesting, especially in those recent years? So first of all, you are probably familiar with the idea that we kind of have a decent idea of what the black hole mass function looks like at the higher mass end, where we have a lot of AGN observations. But as we go into the more so-called intermediate mass regime, what we have is that basically it is hard to observe intermediate mass black holes because they are possibly rarer or they accrete less mass. And so the interesting aspect of tidal disruptions is that they are especially good to illuminate low mass black holes that were otherwise quiescent. And in particular, they would complement the observations of future gravitational wave facilities, for instance, LISA, that are going, in fact, to really observe across the cosmic times those low mass black holes. And in the very near future, with very good observatories like the Vera Rubin Observatory that is going to come, is about to come online like in the next years, we are going to hopefully enhance the amount of tidal disruptions that we observe by a factor of 10 or 100, because now we have roughly 20 events per year. So we are going to get something of the order of hopefully even thousands, and this is going to be a revolution to study the low mass end of massive black holes. But of course, what is very important to really construct a mass function for our massive black holes, once we collect a lot of tidal disruption event observations, is to have a clear idea of what their event rates look like, depending on the environment where those tidal disruption events are produced, on the mass of the central black hole, and so on. And so what I'm going to focus on today is the main generation mechanism, what is thought to be the ubiquitous generation mechanism of tidal disruption events, which is two-body relaxation. So in a very, very short, in very few words, two-body relaxation is basically when we have stars orbiting a massive black hole, and what happens is that stars tag each other's orbit, and it can happen that the orbit of one unlucky star eventually gets into an orbit that has a pericenter that is so close that it gets destroyed. And computing what are the rates associated to those tidal disruption events is really like a very broad topic that encompasses many years of theoretical work typically done through this famous lost cone theory that I don't want to go into too much detail now, but let me just mention, we will go into more detail later, that this lost cone theory that was actually developed basically 50 years ago, like at the beginning, we expect that the tidal disruption event rates would be of the order of a few times 10 to the minus 4 or even more per galaxy per year, while the observed tidal disruption event rates that we are starting collecting in recent years are something like 1 order of magnitude less, or at least a factor of few less, pointing into the direction that maybe this theory has something that is not perfectly fine. It's relatively good, but not perfect. And what I want to stress is that this theory suffers from many simplifications. For instance, the fact that you have your galactic nucleus that is rarely allowed to evolve in time, is typically considered like a static system, or the fact that you assume only one solar mass stars. You make many assumptions just to simplify your life. And so this could be at the origin of the discrepancy. But in particular, what I think has been neglected, and I'm going to focus on today, is the fact that if you look at the lost cone theory, what you typically assume is that you have your population of stars, all stars that do not cross the disruption radius at which you expect tidal disruptions survive happily. Instead, all stars that get inside this threshold radius that for a Milky Way-like galaxy is of the order of like 10 to the minus 6 parsecs, then they undergo the total disruption, the star is ripped apart. But in fact, reality must be more complex, because what you would have is that, first of all, if the star passes far enough from the massive black hole, maybe it just undergoes a little bit of a tidal deformation. As the star gets closer to the massive black hole, but not quite yet to the stage at which it is totally disrupted, it can just be partially disrupted, meaning that only a part of the star is leaking onto the massive black hole. And of course, these kind of partial disruptions can be repeated, because if the core remnant survives, it can come back and undergo another flare, and so on and so forth. Of course, at some point, if we reach the tidal disruption radius, the star will be totally disrupted. And at some point, if the star gets too deep closer to the massive black hole, it would just enter the black hole horizon. And this is pretty obvious, right? So what we wanted to do in this work is actually to assess what happens if we make our lost cone theory more complex and allow those partial disruption events to occur. What happens to the event rates of tidal disruptions we estimate? And just to mention a little bit about partial disruptions, the theory suggests that those could be in principle recognized, because they are expected to fade with a steeper trend in their light curve, even if, of course, observationally you have all the errors, so it's very hard to get a handle on the shape of the slope. On the other hand, we have a few candidate repeating events which point in the direction of the fact that maybe some partial disruptions have already been observed. Actually, to understand better what I'm going to present to you in the next few minutes, I'm going to talk about a bit the lost cone theory. So what is this thing? The idea here is that you define a lost cone, which is a region in the parameter space, typically in semi-major axis and eccentricity, or better in energy and angular momentum of the stars surrounding the massive black hole. And what you get is that all stars that have an angular momentum smaller than a particular threshold can be tidally disrupted, can undergo this tidal disruption. And this happens unless the star is deflected as it is moving towards the tidal disruption radius by two-body relaxation before it gets actually there. On the other hand, of course, this has been defined as the tidal disruption radius, assuming total disruption throughout the years. However, here, what I'm going to propose to you is that, in fact, the right tidal disruption radius should be the one for partial disruptions. Why? Well, because for partial disruptions, we have that a star, after a few repetitions, can be anyways completely consumed. And if it does not, anyways, the kick it received at the pericenter can make it go away from the lost cone. So in a way or another, the star is lost from the lost cone, meaning that we are basically in the same assumptions we would make if we were working into the standard lost cone theory for total disruptions. But so let's look a bit more in detail at what happens in the phase space. So here we have the 1 minus the eccentricity of a star, circular and radial orbits. Here we have the distance from the massive black hole. And what happens is that far from the massive black hole, the movement of a star is typically like this. So what we have is that in each orbital period, a star can get scattered many times by two-body relaxation even before reaching the tidal disruption radius. So if here there is the limit at which we have partial disruptions and here total disruptions, what we have is that a star can basically jump around and go from an orbit that is unperturbed to a total disruption. But if we look at what happens at orbits that instead are closer to the massive black hole, far away, so on more circular orbits, you have more like those jumps. But as you get closer to the disruption radius, the star moves on with very, very nearly adiabatic steps, meaning that the relaxation is very inefficient on these kind of orbits. And so the first radius it would encounter as it approaches basically the massive black hole is always the partial disruption radius, meaning that those orbits of stars that are closer to the massive black hole can only, as a first thing, undergo a partial disruption. And so this is very important because, I mean, in this limit, you would expect that all first TDs are partial. And what is the partial disruption radius, however? So what we did in our work is to assume, to take the prescriptions that have been proposed by our collaborator Tao Ryu, who used GRMHD advanced simulations to understand for each massive black hole and stellar mass what is the disruption radius at which the star is stripped by 10% or 3% or 1% of its initial mass. And in particular, for this work, we selected 3% as a threshold for partial disruptions to occur. And what happens, in fact? So in the first case here, I'm showing a case in which the galaxy is dominated by the so-called full loss cone. So basically, most of the stars live far away from the massive black hole, so they undergo those big jumps in the phase space. And basically, what you are seeing in this plot is the event rate cumulative as a function of the mass that is stripped by the star at the event. So here would be like delta m over m is 1, meaning that you have a total disruption, while here as you go towards the right, you get that the star gets stripped by 50%, 20, 10, or 5% its mass. And what you see is that what you would compute, assuming that you only have total disruptions and neglecting partial disruptions, is basically this line here. And instead, the real total disruption rate is this point here. So it's a factor a few smaller, but not dramatically smaller. I'm nearly done. So what you have here is that instead, as you move to partial disruptions, the total amount of partial disruptions can be much larger, a factor 10 or even close to 100 larger. On the other hand, the dotted line shows you the possibility of repeated partial disruptions, which is basically 0, because basically in this full loss cone regime, it is very unlikely that a star will come back and have this disruption repeated. But what happens instead in more dense nuclei, like the one in our Milky Way, like the ones that are more promising for giving us tidal disruption events just because they are denser? Well, here we are dominated by the so-called empty loss cone, where you saw before that the star would move basically adiabatically and always first encounter the partial disruption radius. So here the outcome is pretty different. The plot is the same as before, but what you see is that you would estimate, neglecting partial disruptions, that this amount, so little less than 10 to the minus 4 events would happen in your system, while the total disruption event that is real, accounting for partial disruptions, is basically an order of magnitude lower. So this is a very significant discrepancy. And on the other hand, in this stage, the rate of partial disruptions that repeat themselves is very large. So at some point, you can have very many events that are repeating, but of course stripping a small amount of mass. So those can be harder, basically, to observe. And yes, so this is very important because it would really significantly affect our event rate in the galaxies that are more likely to host tidal disruptions. And let me just conclude very briefly. So first of all, I want to stress again that tidal disruptions are a great tool to let us study what is the low mass end of the black hole mass function. On the other hand, what we found in this work is that the partial stellar disruptions must be taken into account if you want to compute well your event rate. They can be much more common than total disruptions, even if perhaps they are, of course, harder to observe because they are fainter. And on the other hand, what is very important is that if you do not account for partial disruptions, you can significantly overestimate what is the rate of the total disruption events that you would estimate neglecting those. And so this can actually reconcile at least a bit the discrepancy between observed tidal disruption rates and predicted tidal disruption event rates. And with this, I close my talk, and sorry, I was a little over time. Thank you so much.
So I think we can leave a microphone to the speaker and talking a bit louder for asking questions. Okay, perfect. So if someone has questions for Elisa, please raise your hand. speaker, who's Laura Di Gesu from the Agenzia Spaziale Italiana. So just to remind you, we have 15 minutes for each talk, and to the speakers who I'm chairing, I will give you a sign when it's 5 minutes left and 2 minutes left. So keep an eye on me, I will be there standing.
Okay, so hello everyone. I am Laura Di Gesu from the Italian Space Agency. And I want to thank the organizer for having me today talking to you about learning about active galactic nuclei using X-ray polarimetry. So nowadays it has been almost 2 years that we have in space the Imaging X-ray Polarimetry Explorer. So IXP is a NASA mission developed in partnership with the Italian Space Agency, and it is the first mission ever in space entirely dedicated to X-ray polarimetry. So it is allowing for the first time to measure the polarization in the X-ray band of a variety of astrophysical sources, including extragalactic sources like AGN. And the sensitivity of XP2 polarimetry is thanks to the 3 identical gas pixel detectors based on photoelectric effect that have also imaging capability at low resolution and works in the typical X-ray band between 2 and 8 kV. Okay, so this is my brief introduction about polarimetry. So polarimetry basically describes your astrophysical radiation with basically two observables. The polarization degree, that is the fraction of your light intensity where the electric vector field oscillates in a preferential direction. And this preferential direction is the polarization angle. However, for practical purposes, and this is actually the way the polarization information is encoded in the IXP data, it's always useful to decompose the polarization degree and angle into 3 Stokes parameters that are these 3, E, Q, and U, where E is the total intensity, and Q is the intensity polarized at 90 degrees, and U is the intensity polarized at plus minus 45. However, these two things are equivalent, and they are simply connected by the formula that I'm showing there below. Okay, so as I told you, Stokes parameters are used basically in the IXP data. So an IXP data sets consists basically in a normal photon list, but the polarization information is like recorded in the form of photon by photon Stokes parameters. So at this point, you have basically 2 ways of extracting the polarization of a source. You can use the analytical prescriptions of Kisla 2015, and this is often referred to as making a P-cube. Or you can make a spectropolarimetric fit. In this case, you will have a normal X-ray spectral fit because the spectrum of E is just a normal spectrum. But in addition, you will have the spectrum of Q and U. And so you will have models describing how the polarization properties change with energy. Okay, so let's come finally to AGN. So of course, in the classical AGN pictures, there are different components out of which we can expect X-ray polarized radiation. And one of these is, of course, the relativistic jets, because the emission from the jet is basically synchrotron radiation, and in the case of synchrotron, the polarization is expected to be high if the magnetic field is uniform and ordered. So in this sense, the polarization degree is diagnostic of the magnetic field conditions. Then in the specific case of a relativistic jet, the emission covers a broad range in energies. So by looking at the multi-wavelength polarization, we can learn about how the particles are distributed in the jet. Because if highly and lowly emitting particles are cospatial, they will feel the same magnetic field. So we will have similar polarization in different wavelengths. And finally, the time variability of the polarization is sensitive to the mechanism that accelerates the particle in the field. So all of this is best studied in a particular subclass of blazars that are the high synchrotron peak blazars. So this is like just to remind you of the spectral energy distribution of a blazar that is dominated by the jet emission and comprises two amps, of which only the first one is due to synchrotron, and in high synchrotron peak blazars, basically the peak of the synchrotron falls in the X-ray band. So of course these are natural target for an X-ray polarimeter, and here I'm summarizing I'm listing the high synchrotron peak blazars that have been observed so far by IXP, and I'm going to talk you mostly about Markarian 421. So basically, blazars are bright X-ray sources, so with IXP, day-long observations are typically sufficient to have a detection of polarization. But we decided to go for a strategy of repeated observation to search for long-term variability of the polarization properties. Okay, so this is a summary of the result of the first observation of Markarian 421 in May 2022. So basically, the first time we looked at the source, we had a highly significant detection of polarization. So we had a polarization of 16% at an angle of 34 degrees. And this is basically the result from both the P-cube and the spectropolarimetric fit, that in that case included also nu star and epic data. Okay, so as I told you before, it is useful and it is interesting to put these results into the multi-wavelength context of polarization. And so this is basically a summary of the polarization property of Markarian 421 in May 2022 from radio to X-ray. So the key finding here is that the X-ray polarization was 5 times larger than the polarization in the optical, and then and also at any other longer wavelength. And so this is, I'm showing only this example, but this was found consistently in all the high synchrotron peak blazars that we observed. So how to interpret this finding? So this is an artistic representation of our interpretation. So this finding of a higher X-ray polarization than optical is pointing to a shock acceleration scenario, because what happens is that the compression of the shock is able to order a previously disordered magnetic field. So the X-ray particles are those freshly accelerated, so they are closer to the acceleration site where they feel the most ordered magnetic field. While this is not the case for the particles emitting at optical or infrared light, because they have a longer cooling time, so they are emitted in a region that is larger than the shock region, so they feel an increasingly disordered magnetic field. Okay, so then, as I told you, we looked again at the source, at the same source, to search for variability. So when we looked again at Markarian 421, it was June 2022, and basically we found that the situation had changed. So in 2 observations, separated by 1 day, basically we had no detection of polarization. So it could be that the polarization had changed, or it could be that it is cancelled out by a variability of the polarization angle. And why we thought about this? We thought about this because this is actually a feature that is often observed for blazars in the optical. So it is nowadays routinely observed that the optical polarization angle of blazar can undergo basically full rotations over the course of some days, with rotation rates of the order of few tenths of degree per day. And this is an example of this from the RoboPol campaign. Okay, so I'm making a long story short, but basically the answer is yes. This is actually what probably had happened in Markarian 421. So here we basically took the data and split the observation into shorter time beams of few hours. And basically when you do this, you see that actually there is a rapid and monotonic rotation of the polarization angle, occurring over both the observations. The interesting thing is that no similar rotation is seen in data at longer wavelength. So the optical and radio polarization angle were not rotating. And once you do this, the polarization degree is constant with time, and it is actually similar to what was found in non-rotating epochs. And finally, also while the angle was rotating, also the spectrum was changing, and was changing in a harder when brighter fashion. So when the spectrum is brighter, when the luminosity is higher, the spectrum is the hardest. Okay, so how to interpret this? So at first we tested whether a random walk of the polarization vector could explain the observed rotation. So if it was just a random variability that by chance occurred in a full rotation. And our simulation showed that this is very unlikely for the observational constraint that we have. So at this point, we have to think to something deterministic, so to actual physical structure in the jet. And so the interpretation of this, it is shown in the artistic representation there. Basically, we thought that the shock, so a shocked blob, is propagating through a helical magnetic field. We keep thinking to a shock because it is still true that the polarization degree in the X-ray is larger than at longer wavelength, as in non-rotating epochs. Okay, so now let's come to another elements in AGN that can produce X-ray polarized radiation, and of course, another example is the X-ray corona that is responsible for the primary X-ray emission in AGN. So of course we think that in the vicinity of the black hole there is a corona of hot electron that is able to upscatter the disk photons to the X-ray band. So this is a case of scattering. So in the case of scattering, we expect polarization if the scattering geometry is not symmetric. So in this sense, X-ray polarization is a diagnostic of the geometry of the corona, which is still an open question, and it is of course connected to its physical origin. All of this is best studied, of course, in type 1 radio quiet AGN. Okay, so here I'm summarizing the observation of radio quiet cipher 1. So this case is a bit more challenging for IXP because these sources are fainter, so typically week-long observations are needed. Also, the X-ray spectrum is more complex. There are more than one components contributing to the spectrum, so typically multi-satellite observations are useful. So here I'm summarizing the type 1 AGN that were observed by IXP. And so what you do, you basically compare your polarization with simulations of coronal geometry that are done through Monte Carlo radiating transfer code, and there I'm showing some examples of possible geometry that could be tested. So we had basically an upper limit in two sources, but our best case is NGC 4151, but I'm not going to tell you anything about this because there will be a talk dedicated to this by Vittoria Gianolli. So I'm just showing you the case of the upper limit in 5 MGC 52316. So here the polarization is undetected, but basically you can see from the contour that the contour plot prefer a direction that is like parallel to the oxygen 3 emission, so perpendicular to the disk. On the right, you see the results of the simulations of different coronal geometry compared to the limit from IXP. Basically, you have that a spherical corona is always consistent at any disk inclinations, but but in this case, the slab corona is preferred because basically is consistent with the limit or only at inclination lower than 50 degrees, and it is the only one between this that predicts a polarization angle that is perpendicular to the disk. Okay, and the last example that I'm showing you is the case of the torus. The torus is of course an X-ray emitter because of cold reflection. So in this case, we expect a polarization. I mean, if the geometry is indeed toroidal, that is definitely not symmetric. So that's why we expect a polarization from the torus. And this is, we had only one example of this that is best studied in type 2 AGN, and this is the observation of the Circinus galaxy. Okay, so this is the spectropolarimetric fit of the XP and Chandra data of the Circinus galaxy. Of course, there is more than one component in the spectrum, and they were all taken into account, but from the spectropolarimetric fit, we extracted the polarization of the cold reflector that is polarized at a level of 28%. So this time we have the opposite of before, so the polarization angle is perpendicular to the radio jet, so roughly parallel to the disk. So, and so you can use this information to extract some geometrical properties of the torus. So this is a geometry that you can simulate. And on the right, you have some results. So depending on the inclination of the observer and on the torus opening angle, and from the observational constraint, you derive an alpha opening angle of 45 and between 45 and 55 degrees. And this is well consistent with the basic prescription of the unified model of AGN. Okay, so I think I've used my time, so I leave you with my conclusions.
Thank you very much for your talk. If someone has a question, please raise your hand. sorry, this is bed sharing. I forgot to mention the fact that it would be nice when we ask a question or discuss to say who we are, because maybe we don't know each other. So thank you.
Okay, thank you. So, hi everyone, I am Federica Ricci and I'm happy to be here today. This is my first young AGN meeting. And so today I will present you a work about the near-infrared view of the BLR and in particular the effects of obscuration in X-ray selected local AGN, and this is inside the bus data release 2. So for those of you that are not familiar with BUS, BUS stands from Swift Bat Spectroscopic Survey. And basically, the BUS survey is an international effort to gain spectroscopic information of the local accreting supermassive black holes that are detected by the Swift Bat satellite. That is an all-sky survey that is performing a survey in the hard X-ray band, so 14 up to 195 kV, more or less. And so here I am just listing basically the papers that went out from our data release 2 that happened last year. And we got like 800, more than 800 spectra, basically covering all the AGN from the 70-month catalog. And so we have a rich multi-wavelength data set covering the optical, and then we also have X-ray information from Claudio Ricci paper in 2017, and then we also have the coverage in the near-infrared, which is the one that I will present you today mostly, but I am also highlighting like the important papers that are pivotal for my work as well. So the goals of my work in this paper are like basically two. So the first question that I wanted to ask is whether H alpha is reliable to get the black hole masses in AGN, particularly using the so-called single epoch virial techniques that are like the Green and Ho 2005 relation that are based on the full width of maximum of H alpha and the line luminosity of H alpha, of the broad H alpha. And the reason why this question is important is shown here in these two plots, in which two different teams explored the black hole mass stellar mass relation for local AGN, mostly using the black hole masses from the H alpha line, and they found that the AGN are undermassive of about 1.2 dex with respect with the expectation from the normal black hole host scaling relation. And a similar effect is shown here by Kos and collaborators in 2017, in which they are comparing basically the black hole mass from the black hole sigma relation and the ones from the H alpha line, and again they are finding that they can be up to 1 dex undermassive with respect to expectation from the black hole sigma relation, and you can see that this effect is more prominent when the H alpha equivalent width is lower. So these two results can either can tell us either that the black hole scaling relations for active galaxies are different than inactive galaxies, otherwise you wouldn't expect a difference in the black hole masses, or that maybe H alpha is not that reliable for AGN, especially when there might be some level of obscuration. So the first goal of my what happened? Apologies. This is... Ok, devo toccare ogni tanto, va bene. Okay, so the first goal is to try to compare what we can get from the near-infrared and the alpha measurements in CIFER 1s up to CIFER 1.9 that are the ones that show only broad H-alpha line and not other broad lines in the optical, in order to understand if there are biases that appears when the obscuration is increasing. In particular, when we want to characterize the two main parameters that enters inside virial mass estimate, that is the broadline velocity and the broadline radius. Then the other important parameters that enters the virial relation is the so-called virial factor F that is shown here, that basically allows us to use a proxy for the BLR velocity, which is often the full width of maximum of the broad lines. And some works have performed statistical studies on broad lines AGN, and that found that, as you can see in this plot from Mejia, Restrepo and collaborators, there is an anti-correlation between the virial factor and the full width of maximum measured in several lines, H-alpha, H-beta, magnesium 2 and carbon 4. And this anti-correlation basically can be explained if we are viewing the BLR under a certain inclination angle, so that the line is getting broadened when the inclination angle is increasing. And what all these works that are shown here, of course, are based on broad lines AGN, so the ones that show broad lines in the optical. So the question is, what is the virial factor for the ones that do not show optical broad lines? Because the virial factor is basically encapsulating all our knowledge about the geometry and dynamics of the BLR. So the question is whether it is different in different types of AGN. And a way to try to get the broad lines for these sources where we expect more obscuration, more dust, is to try to look at the near-infrared. So here I'm showing you a spectrum, an average spectrum from Glickman and collaborators. And here you can see that there are some prominent lines that we will I will focus on those lines, the helium 1, the Paschen beta, and the Paschen alpha, because basically the Paschen lines are among the strongest emission lines in the near-infrared. We want to use the near-infrared because we expect less effect of dust absorption than in the optical, and indeed in some cases when you have enough signal to noise and enough spectral resolution, broad lines have been found in the near-infrared also for sources where they didn't show optical broad lines in about 30% of cases. So now you understand that my second goal was to try to build a statistical sample, obscuration unbiased, to try to get the black hole masses and then the virial factors for both CIFER 1s and, let's say, CIFER 2s, using these let's say, virial estimator that is based on near-infrared lines and on the hard X-ray luminosity. And so we will get the so-called, I am calling this M line, which is a virial estimator of the black hole mass, and then I can estimate the virial factor as basically the ratio of one black hole mass that is depending on the virial factor and one which is independent from it. Okay, so This is why I joined the BUS collaboration, and inside this collaboration, I basically I took part while I was a fellow in Chile, and there was no COVID yet, so I was lucky that I could go actually, to get my data. Here I am at the Magellan, and so we observed about 60 AGN from the Swiss BAT survey, and here you can see my data in the hard X-ray redshift plane compared with the other bus coverage. So we end up with a database putting together all the three samples of about 300 near-infrared spectra, and it is thank you. The largest near-infrared database so far. And in my work in particular, I focused on the characterization of, as I was saying, of these lines, because I wanted to study, to characterize the BLR properties for these sources. And putting all together, we found in about 30% of sources a near-infrared line, broad line in at least one of these transitions. And so we end up with a nice database. But first of all, let's see what the H-alpha in the bus sample is telling us. So here I am showing the results from Mejia Restrepo 2022, and on the left you can see the full width of maximum versus NH, and on the right the ratio of the broad H-alpha luminosities to the hard X-ray luminosity versus NH. So we wanted to understand how the H-alpha is performing with increasing obscuration. So here you can see actually the H-alpha for if you focus on the red points, which are the Cipher 1.9, you can see that the full width of maximum is not underestimating the BLR velocity, at least until this level of NH of about 23 in log units. And so this is fine. The full width of maximum of H-alpha is a good proxy for the BLR velocity, while the quantity that is getting biased, is shown here on the right, is the broad H-alpha flux that you can see there is a drop occurring at an H level, let's say between 21 and 22. And this is introducing a bias, of course, in the black hole mass estimates when you use only H-alpha line, which is of the order of 0.3, 0.4 dex. So the next question is what can we learn instead from the near-infrared? So the first result, the first take-home message is that when you measure the full width of maximum of the H-alpha and of different near-infrared lines, basically you are getting the same information. So the near-infrared lines and the H-alpha are probing the same velocity field. And there is a nice, you can see, this is the one-to-one relation. So there is, of course, there is some scatter, but more or less the things are probing the same velocity field. And for this reason, we can, thank you, we can use these, in the next slide I will show this near-infrared as the collection of detection of either one of the line or the mean, if there is more than one detection. So here you can see the same plot as before, but for near-infrared lines. And as, again, we can see that the full width of maximum of the near-infrared is not affected by the level of obscuration, at least until of an H level of 23 in log units. Here the plot is divided according to the Cipher classification. And also for the near-infrared line, the quantity that is getting biased is the line luminosity, and there is a drop here occurring at around 22, and I'm not showing this in the presentation, but we can see that this NH threshold is moving a bit when you go to longer wavelengths, as you expect from naively from the fact that the dust effect is less when you move to longer wavelengths. And so the message is that if you have a source which is like Compton thin, should use a less biased proxy for the radius of the BLR, for instance, the hard X-ray luminosity, as I was proposing back in 2017. And now I'm showing we can see for the first time the distribution of the virial factors for all the population of Seifert, both Seyfert-1 and up to Seyfert-2s that actually show the broad lines in the infrared. And you can see that we don't find any statistical difference in the distribution of the virial factors, so they are basically the same for the whole population. Then I will go faster, and here I am showing these two different black hole mass estimators, and we can see that the two more or less agree, with some scatter, which is of the order of 0.5 DEX, which is, however, expected since both the black hole sigma relation and the virial-based black hole mass estimators do suffer from intrinsic scatters as well. And you can see that the points are colored according to the measured full width half maximum of the broad line, and there is indeed some gradient here, probably telling us that indeed the line is getting broadened when the inclination is higher. And then, let's say my last slide is here. We wanted to understand whether the virial factor, so which is basically the difference in these two black hole mass estimates, does depend on additional parameters. So we don't find any dependence on redshift or NH, which is good actually. And we find a weak anticorrelation with the virial mass, which is, however, expected given the fact that the black hole mass depends on the full width half maximum squared. And basically, I am done, so I can take questions and leave my summary here. Sorry for being a bit late.
Microphone. So, if you have questions, please welcome Cheng Xin from the Columbia University, who will talk us about tide unpeeling.
You want to try your laptop?
So hi everyone. All right. Okay. Hi everyone. I'm Cheng Xin. I'm a graduate student visiting from Columbia University in the astronomy department. So I guess this isn't my first time attending Young AGM, but previously I've been on Zoom. They're always in Europe for some reason, which is great. So today I want to talk to you a little bit about dynamical process again in the galactic nucleus. So I call this tidal peeling events. The name would become more apparent later on. But it's basically low eccentricity tidal disruption events of a star by a stellar mass black hole. So these are the collaborators, including my advisor, Zoltan Heyman, and postdoc Taiho Rio. I see some mutual collaborators. Yihan Wan, who's a postdoc at Nevada Center, and Professor Roselva Perna at Stony Brook University. So why do we care about this? We care about micro TDE. It's micro because the black hole is a stellar mass black hole. And we care about these type of disruption events in two major environments. One of this is the fact that stars and compact objects are very abundant in stellar clusters, near AGNs, or even in the disk of AGNs. So we expect stars in clusters in the galactic center to be preferably massive. So in this work, I would be considering stars with a range of stellar masses. So what motivated me the most about this work is that you can have this type of events in the AGN disk, because stuff can be captured onto the AGN disk or be formed through in situ star formation in the disk. And this has becoming a very interesting topic these years due to LIGO detections, that some of these black hole binaries that we see in LIGO could not have been formed without an AGN disk. So that's the current theory. Just to summarize it, the type of encounter, I'm talking about close encounter between stars, preferably a sun-like star or a massive star, and a black hole in AGN disk environment. So these type of binary has been investigated in encounters with high eccentricity, which is typical for any micro TDE or TDEs. When people talk about it, they think eccentricity of 1 or near 1. So here I motivate another type of scenario. Sorry, these are just two particular examples of people simulating micro TDEs that are super eccentric. But here I motivate the scenario where this encounter could also have low eccentricity for three main reasons. First, some observational work suggests that compact binaries, even though these observational work are on stellar mass binaries, they could be near circular, especially when the binary gets very compact. The second motivation is hydro simulation has shown in the AGN disk, binary can be shrinked by gas dynamical friction, and the most stable eccentricity in that scenario is either near circular or near 0.4 or 0.5. And the last motivation is actually work by the collaborator. My collaborator is that three-body interactions in star clusters can also induce close encounter between star and black hole in a low eccentricity manner. So that's what we're doing. We're simulating this process for the first time, and the code of choice here is Phantom, which is a publicly available SPH code for this simulation. So the setup, we first start a main sequence star. So I take the stellar profile from MESA, which is a 1D stellar evolution code, to have a more accurate representation for the stellar profile compared to what's being provided in this 3D simulation. And the black hole will be represented by a sinc particle with accretion radius of 100 Rg, meaning gravitational radius, And of course, this number could change depending on what kind of star or black hole that you have. So I would like to remind you of the definition of tidal radius. So this is also the radius roughly when mass transfer should be expected to occur in this type of events. So in particular, in my project, I consider a few variations in the initial condition, and I want to observe how the orbital property and also accretion process and stellar deformation would change depending on these initial conditions. So first I would vary, so black hole mass is fixed at 10 solar mass, but I would vary stellar mass from 1 to 15 solar mass. It could be even larger if you consider some cluster stars, but this is the range that I consider. Sorry, but there's noise. I see. Okay, great. And the range of eccentricity I consider is from 0 to 0.6. And finally, I would also vary the distance between the star and the black hole, or you can call this impact parameter. So beta corresponds to, so beta varies from 1 to 0.33. It's kind of counterintuitive, but for smaller beta, you have a wider separation. So this corresponds to peri-astron distance from 1 to 4 times tidal radii. Okay, so finally I explained the name of tidal peeling. As you can see, this is a typical system of tidal peeling where the mass of the star is slowly stripped from the tidal impact of the black hole. So hence the name tidal peeling. And mass loss happens at all of the Lagrangian points here. I drew the initial potential surface. That's the light blue loop over here. And some of the mass are lost and form spiral arms around the system, and some of them would be accreted onto the black hole or remain bound to the black hole and form this accretion disk within the initial equipotential surface of the black hole. So in this particular case, the star is totally disrupted after about 4 pericenter passages, but this isn't always the case. You could also have partial disruption, just like in normal TDE that Elisa told us about earlier, depending on the initial condition. So in some cases, the remnant could survive for hundreds of orbits before it gets severely disrupted. So this is just a summary slide of the video, so I would skip the slide. Okay, so this slide might look a little busy, but let me walk you through it. So in order to study these phenomenon quantitatively, I investigated a few key parameters, including mass accretion onto the black hole, the mass accretion rate, FRM is a fraction of mass removed from the star, and a couple of orbital properties such as the separation, the time evolution of eccentricity, and semi-major axes throughout the simulation. So the first model here is the one that I've shown you in the video. So we have a slightly eccentric system, and the second one is a more eccentric and also a wider orbit system. So the key property that I like to focus on in this talk are the mass accretion rates. But if you're interested in why the other properties evolve like they do, you're welcome to talk to me afterwards or read the paper. A few key things I want to point out here is mass accretion. First, mass accretion rate is typically super Eddington in this case. That doesn't mean these sources can be seen in reality, so I will introduce other sources of luminosity later in the talk, but this is a key one. And you might notice these periodic flares in the more eccentric case. So we observe these periodic flares signatures only when the system becomes more eccentric. So for a fixed stellar mass and fixed separation, we only observe these periodic flares when the system is eccentric. So that's first interesting observation from this work. And the fact that the orbital evolution fluctuates just means the orbit deviates from Keplerian. So going back to m dot, so next we want to investigate how those parameters would change depending on initial conditions, right? So going back to m dot, so in this figure, I show you for the one stellar mass initial condition, how m dot would change depending on the initial eccentricity and pericenter passage. So the crosses here represent total disruption. So first you can see for the circular system and the most compact system here, the star would be totally disrupted, even starting from the first orbit. Thank you. So first, second, and third orbit just means at the moment of first, second, and third pericenter passage. So the general trend here would make sense, which is if you have a wider system or have a more eccentric system, m dot is smaller. So if you have a more eccentric system, so we start all of the orbit from the epicenter. So if you have more eccentric system, that means the orbit would start off wider. And for the most wide and eccentric system, we see that m dot are 0. So these are the empty circles here. But that doesn't mean that mass accretion would be absolutely 0, because from the last page, we see that the periodic flares occurs roughly right after each pericenter passage. So at the moment that you capture this, m dot could be 0, but that doesn't mean there's 0 mass accretion onto the black hole. So I also show another set of results. So these are m dot as a function of stellar mass versus eccentricity and pericenter passage. So I want to show you how the result would change if we have a different stellar mass. So I'd like to point out that the definition of mass accretion rate, so this mass accretion is calculated from the amount of masses accreted to the black hole normalized to the stellar mass. So m dot here, if you see any variation in the vertical direction, that should tell you some kind of variation in the stellar profile, because m accrete is normalized to the stellar mass. So what does that mean? Actually, we don't see a lot of variation in the vertical direction, except for the solar mass star, in the case of the solar mass star. So this lack of trend tells us for the more massive stars, their stellar structure should be relatively similar. I mean the density profile, and this is exactly what we see from the stellar evolution code. But the more massive stars are more likely to be tidally disrupted because they have a larger stellar radii. If you're a more astute listener, you should ask, for the 10 solar mass and above, the tidal radius is just the stellar radius or even larger. So practically we're simulating. So here we're using a different stellar mass to kind of parameterize, different separation to kind of parameterize the distance or the tidal radius between of the system. But you should realize that we're basically simulating a common envelope scenario when it comes to more massive star and when the separation is very compact. That makes sense. So that's what I want to say about the accretion rate. If that's the only source of luminosity, great, we should point our telescope at it, but it's not. So thank you, I'm almost done. So a couple of things that I'm omitting, which are very important in reality, but I'm omitting in the simulation are first, since the accretion rate is super Eddington, we will most definitely have very strong disk outflows from the accretion disk formed around the black hole. But this medium is very optically thick, meaning that the photon might never escape. For the cases that the star is completely disrupted, we would expect the diffusion time scale to be 10 to the 5 years, which is similar to the photon diffusion time in the sun, if you remember that. There could also be jets launched from either the accretion disk around the small stellar mass black hole or around the bigger AGN disk. So that could maybe clear out the environment to make the event more visible. And last, I also want to point out that this binary could also be accreting additional masses from the disk, depending on what kind of disk you're assuming. So there might be some controversy in how you can calculate these numbers, but I'm quoting these numbers from some analytical solution of binary accretion in the AGN disk. by Hiromichi Tagawa, who was actually a postdoc at Columbia. And from his prescription for a 1 solar mass star and a 10 solar mass black hole, roughly the star would be accreting at 10 to the 3 Eddington, and the black hole would be accreting at 10 to the 2 Eddington. So that's a thing that we shouldn't ignore too. So finally, I want to show you the rates. The rates of micro TDE in the AGN disk is roughly 10 per gigaparsec cubed per year. But this is, and this should be even lower in clusters. But this has huge error bar because we only have 2 observational candidates for micro TDE. So just keep that in mind. But compared to the rates of TDE, which is 10 to the negative 4 roughly per galaxy per year, so the takeaway point, I think, is these events could be eventually visible, but obviously we need to come up with a lot more self-consistent model with all these extra physics, and only the most luminous source may be seen in the future. So since I'm out of time, I'll leave you with the conclusion.
Thank you very much. If you have a question, please raise your hand. Going back on time perfectly. So please welcome Antti Rantala from the Max Planck Institute for Astrofisica.
Okay, can you hear me? Yes? Yes, no. Yes? Ha. Okay, so I'm Antti Rantala from Max Planck Astrophysics, Germany. So today I'm talking about a new simulation code I developed. So basically this is N-body dynamics, and one of the first applications, so stellar disks around massive black holes with this code. So, okay, very brief outline. As I said, I'll introduce my new simulation code Bifrost, which is different from the previous simulation code people maybe know me better about. So that was the Ketu code, which was intended for massive early type galaxies and supermassive black holes, but I leave talking about Ketu to the other people here in the audience who will continue. So okay, this is about Bifrost, so smaller scales. Okay. So basically, stellar dynamics around black holes. So this is more than just like two-body star orbiting a black hole. So basically, within an influence radius of a massive black hole, there are by definition from hundreds of thousands to billions of stars. So, as opposed to like Keplerian motion, Newtonian relativistic precession effects are important. Of course, because of the stellar distribution, also like collective relaxation effects are important, starting from, of course, two-body relaxation, and then more complicated stuff like scalar and vector resonant relaxation, which operate in the nuclei. Then, of course, if there are stars, there are binary stars, typically. And with the presence of a massive particle, the binaries can experience these von Siepel-Lidov-Kozai eccentricity inclination oscillations, which changes the orbital properties of the binaries and may even lead to enhanced rate of stellar mergers from the binaries. Then, of course, single and binary stellar evolution operate, not just point particles, but evolving stars, stellar mass loss, and formation of compact remnants also near the black holes. Then, of course, something that is interesting for observers, so transients both in electromagnetic and gravitational waves. So, as we heard, tidal disruption events and partial tidal disruption events, and of course, plunges of stellar mass black holes into the massive black holes, gravitation waves, intermediate mass, and extreme mass ratio in spirals. Okay, a wish list, what one needs to properly simulate this environment. So, this is not a hydro talk, but we still have many ingredients. So basically, accurate gravitational force calculation for at least 1 million particles. High order time integration for great accuracy. And then also specialized integration techniques for subsystems. So basically binaries, close flybys, hierarchical triples, small clusters around black holes. And this is what goes into like numerical techniques, parallelization and hardware. Then about like physics, you want to have, of course, you want to be post-Newtonian. You're near a massive black hole. Then stellar evolution. This is something of a like subgrid stuff. And basically prescriptions for TDEs and stellar mergers, as already mentioned earlier this morning. So how does the code Bifrost fulfill this? So okay, first I want to mention about the name. So original version is called Frost, from the fourth order forward symplectic integrator I use, and with binaries, Frost becomes Bifrost. So this is a GPU accelerated MPI parallelized direct summation N-body code, capable of, at the moment, few million particles at the same time. I mentioned the fourth order, this new integrator we have. Then we have various techniques for these binaries and flybys and so on, Kepler solvers, and something called algorithmic regularization. The equations of motion are post-Newtonian up to 3.5 order, so high order in these subsystems, small ones, and then PN1 everywhere in the simulation domain, so that like we capture the proper relativistic precession effects everywhere in the simulation. We have coupled the code into the new fast stellar population synthesis code 7 for first single stellar evolution, but now actually also with the binaries, and mainly because this is written in C++ and not old Fortran. And of course, we have simplified prescriptions for stellar mergers and TDEs using the tidal radius prescription and some corrections which I actually got from Tehoru, mentioned third time today. Okay, quickly about the integrator. So basically, this is a momentum conserving alternative for the traditional Hermite integrators which the N-body people use. So this is manifesting momentum conservation because all the kicks are always pairwise and synchronous, so no active and non-active particles. So basically Newton's third law is always fulfilled. Strictly positive integration substeps, as opposed to like Yoshida type symplectic integrators where you always have negative steps. And of course, negative times substeps are bad for like if you have like dissipation or gravitational waves and so on. And then hierarchical integration, the rapidly evolving parts of the system actually decouple from the slowly evolving parts. So basically, this method becomes really efficient in integration if your system has a really large dynamical range. For example, if you are orbiting a supermassive black hole in a stellar system. So a really quick walkthrough around the integrator. So this would be the second order leapfrog. You have kicks and you have drifts. This is how you move the particles with your Newtonian accelerations. In the fourth order, it looks like this. You still have your kicks, you have your drifts, but you have something called a gradient kick, which is a little bit more complicated, but nothing like drastically difficult. So basically, this is what the Frost code is using. So this is the hierarchical version, which I actually derived. The original integrator has been used in the literature, but mostly in other areas of physics and not astrophysics. But this is something completely new. So this has been now extended to have these subsystems, so it becomes a bit more complicated, but it works, yes. Then the subsystem integration proceeds with these specialized techniques as well. So we have a subfor for arbitrary binary fraction in the code, so basically every particle can be a part of a subsystem. Only a few other codes can actually do this. So as I mentioned, Kepler solver, but then we used algorithmic regularization as in the Ketu code. Well, it's not the same version, but a re-implementation. So the main ingredients I just list here are the time transformed equations of motion to get rid of the Newtonian singularity, specialized coordinates for accuracy, and also this Krag-Bullier-Stör extrapolation method to have your user-defined accuracy for your integration. So this is guaranteed accuracy. So, okay, maybe I'll skip the details for speed. So now about the application. So evolution of eccentric aligned stellar disks around massive black holes. So of course, this is a little bit connected to like the mysteries of the Milky Way center, the S-stars and the disks there. So this is based on a paper submitted recently, soon to be accepted. So it's this one, you can check it on arXiv. So you know the circular disks, solar system-like. Then you can have eccentric disks in which the stars move around the black hole on eccentric orbits. But I'm talking about the third case, in which the eccentricity vectors are absidially aligned. So these systems, if you're much, much less massive than the black hole, these systems are unstable. This is the so-called Madigan's secular instability. Then, if your stellar system is actually much more massive than the stellar cusps around the black hole, this is actually stable. So this is the M31 double nucleus. But what happens in between? So already all the cases in the extremes as like massive disk and not so massive disk, it's very complicated. But we wanted to study this in the intermediate mass regime. So we expected that the disk is still unstable, but maybe the mechanisms is different, and this is actually the case. So our initial conditions look like this. We chose the Milky Way mass black hole, Milky Way nuclear star cluster as an external static potential. This becomes important in the caveats. Disk masses from it starts from the observed present-day Milky Way center parsec scale disk from like around 8 times of that. We try very different, very top-heavy IMFs based on observations of the Milky Way center, and 9 different initial eccentricities to like almost circular to like almost radial disks. We have massive binaries in the disks, of course, because our code can handle those. Massive stars preferentially, of course, in binaries. Then we have some binary properties for those, but not going into details. So why we did this? So basically, the present-day Milky Way disks, because they are so top-heavy, they have been more massive at the time of their formation. And most of the studies of the dynamics of these disks actually concentrate on these present-day observed ones. Then, of course, there are other simplified assumptions in the literature, so people haven't been able to run this with a single simulation code. So people usually do code switching. So first, simulate the eccentric disk, then switch to like Hill's mechanism kind of stuff, so basically 3-body encounters in which a massive black hole unbinds the binary. And then finally people run a relaxation simulation, so 3 different setups. We can do everything at once. Okay, then about the disruption mechanism. So basically disk mass increases to the right. X-axis is the distance from the black hole, and y-axis is the precession rate of your disk. So when you're really close to the black hole in the low mass disk case, you have like PN precession, prograde, and because of the nuclear star cluster mass precession, this process is retrograde. And this is an unstable literature case. This is the Madigan's instability. But when we increase the disk mass, we actually see that the picture becomes much more complex, because the disk's self-contribution to the orbital precession starts to become important. So first we have these alternating regions of precession in the disk, and finally, with very massive disk, actually the disk precesses mostly prograde. But it's actually very unstable because the outer and inner parts of the disk precess at different directions, and the disk disrupts in a time scale of a megayear. So after the disruption, the orange one is the IC, and the blue one is the result. And you can basically see that the resulting eccentricity distribution in the disk is almost independent of the ICs. The only difference is that, like, if you're initially very eccentric, you will have a secondary high eccentricity peak at almost radial orbits. And these are the sources in which the black hole at the center is fed with binary systems for Hill's mechanism to break. So we have, of course, these Hill's breakups. I have an animation there, but that's after my conclusions, not to waste time looking at the animation. So we have tens of hundreds of these Hill's kind of unbinding events, so high velocity stars. And these happen quickly after the disk disruption. If you look at the plane of the sky where these escaper events actually go, they are strongly anisotropic, which is a signature of this kind of approaches. Well, we have also TDEs, but compared to like 2-body relaxation and so on kind of feeding mechanisms, actually most of the TDEs occur from the captured Hill's companions. So this way, actually, the tidal disruption rate is really high, but only for like 1 or 2 megayears. So we can reach tens or up to like several hundreds of TDEs in these simulations, very strongly depending on the IMF, we assume, and also the disk mass. Then about, does our simulation results look like the Milky Way center? So basically we can have tens of B-type simulated milliparsec stars compared to the famous S cluster at the center of the Milky Way, so that's a rough match. But we also see that like we go less top heavy, we get more S stars, but then the match to the present day disks becomes worse. Because, well, basically the Milky Way center is very rich in O and Wolf-Rayet stars, and the number of T's goes down. Okay. Then about importance of PN and the background modeling. So basically, if we don't include PN, resonant relaxation operates strongly, and we get a thermal distribution. which is close to observations. But this is wrong. World is post-Newtonian and not Newtonian. So basically ignoring post-Newtonian effects can lead to too good to be true kind of results. Always use PN close to black holes. So basically, the thing that we are missing a relaxation process in our simulations, and this is the fact that we use the static Milky Way potential, and not to actually live particle distribution for the nuclear star cluster. It's doable, but it vastly increases the computational cost of these kind of simulations. So this is future work. So conclusions about the eccentric disk. This is the simulated S cluster. It looks like the actual one. I can explain some of the differences if needed. Okay, so basically we have uncovered a new precession instability. We can successfully reproduce some of the properties of the Milky Way center, but the difficulty is to simultaneously match all the various constraints. So apparently, more complex ICs are needed, so multiple disks, IMF gradients, maybe starting from actually molecular cloud infall kind of simulations. Then the Bifrost conclusion, this is my last slide, so this is a really promising tool I'm keeping to develop. First applications like this disk stuff is published. We have also studied IMBH growth in a runaway collapse scenario. And at the moment, I'm preparing beyond million body simulations of nuclear star clusters with all of these machines. Thank you. And as my last slide, I promised you the Hills mechanism, and we can.
So while watching this movie, no, okay. Does anyone have a question?
Hi, thanks for the nice talk. Hi, Matteo. So I have a few questions. So the first one is about the angular distribution of the hypervelocity stars.
My name is Christian Partmann. I'm a Ph.D. student at the Max Planck Institute for Astrophysics in Garching, and today I'm going to present my simulations of black hole feedback in dwarf galaxy simulations. And I think traditionally the dwarf regime is not what people think about when feedback from black holes is discussed. And I think that's for good reasons, because most of the observations of massive black holes are in the high mass regime. These are dynamical detections. But what's going on in the low mass regime is absolutely not so clear. With much improving observations now, there's now also mounting evidence that also in the low mass regime we actually have black holes, which are correspondingly smaller. So they're expected to be in the intermediate mass black hole regime and in the regime which is traditionally the dwarf galaxy regime. So the reason why we do not really know what's going on in this ballpark is that the physics there changes qualitatively. So the potential wells of the galaxies are much shallower. There's not a clearly defined dynamical center of these systems, so we do not even know where the black holes are. So we have recently published a study where we just looked at the sinking of black holes in these low mass systems, and we find that a lot of them might just not sink to the center. So they might be sitting in places where the gas densities are even lower than the gas densities in the center of dwarf galaxies, such that the expected accretion rates are low, and if the expected accretion rates are low, also the X-ray luminosities, for example, are just below the observational thresholds that we can detect. So, in conclusion, it's really difficult to figure out what's going on here. It's very difficult to figure out the occupation fractions and mass functions. But this regime is super interesting, and we actually want to know something about it, because as, for example, reviews by Jenny Green has pointed out, if we want to distinguish between the formation mechanisms of black holes in the early universe, the seeding mechanisms, dwarf galaxies might actually help us, because the different mechanisms that are on the table here, that's, for example, the gravitational runaway scenario that we have discussed a bit earlier today, but there are also other seeding mechanisms, the POP3 scenario, the direct collapse. They make very different predictions for the black hole occupation fraction, masses, properties in the dwarf galaxy regime, at least if we find that certain assumptions that we have about this regime are true. So as a theorist, my approach is to now look at what black holes do in the dwarf galaxy regime. In particular, we want to know to which extent black holes can grow. If we find that they don't grow, that kind of gives us a good argument to believe that the black holes that we see in dwarfs today give us a good idea about the black holes in the earlier phase of dwarf galaxy evolution. We would like to understand what fraction of time we expect black holes to be active, to be visible for observers, such that we can estimate like to which extent we only see the tip of the iceberg. And we would like to figure out where the black holes actually are expected to live, so whether they sink to the center, whether they stay there, or whether they just wander around, such that we kind of have to be more flexible in our search for them. Okay. The simulation framework that we choose here is the Griffin model of the interstellar medium. So this model is designed to give us a pretty good approximation of the resolved multi-phase interstellar medium. We do this by pushing resolution down to the scale such that we can resolve the individual feedback events, the supernova feedback, the photoionization from individual stars. We of course also include other ingredients that are super important to get a realistic baryon cycle in a dwarf galaxy, and something that is very new in this type of simulations is that we realize the full initial mass function from the high mass end, a few hundred solar masses, down to the hydrogen burn-in limit of just 0.08 solar masses. So each and every star particle in our simulation actually represents a physical stellar object. Modeling the interstellar medium in a as complete as possible way is of course just one side of the coin. Now we also have to worry about how to get the black holes in the picture here. So because we have enough resolution to resolve the Bondi radius of the typical black hole masses that we're looking at, we chose to go for a sinc particle accretion approach. So the basic idea is we have particles around the black hole, and we look at their properties inside the maximum accretion radius, which is set to 1 parsec, and check if the angular momentum of these particles and the Bondi-Heulitten radius of these particles are smaller than the distance to the black hole, here like in a schematic way shown in blue. So when these three criteria are fulfilled, we just remove the particle from the simulation and assign it to the not resolved accretion disk. So in this way, we can get away from the assumption that the accretion flows are spherically symmetric, as usually is assumed in the effective Bondi models, which are used in many cosmological simulations, and we can have a more accurate description of the accretion mechanism also below the Bondi scale. So what's going on the accretion disk then is of course another thing which I will not go into here, but we also have a prescription that for each and every accreted particle gives us the accretion rate onto the black hole, which will become important later. Because we have the individual stars in our simulations, we can now also think about improving the dynamics in the vicinity of the black hole. And we do that with the code that Antti has just mentioned. In particular, we have regions around each and every black hole where we switch to something that is almost the full n-body dynamics, and not relevant for this particular application right now, but in principle we can of course also follow the post-Newtonian forces between black holes in situations where we have multiple black holes in the simulation. The reason why we think that is important is that it automatically gives us resolved dynamical friction, which is very important if we want to understand whether the black holes sink. Again, that is something that we have been looking at in a different context. It was recently published, and as I will show, this is also important in this case. On the other hand, improving the dynamics also allows us to study things like the dynamics in a nuclear star cluster if it forms in our simulations. That is something that Jesse will talk about later, and future applications of that could also be to look at tidal disruption events in a full dwarf galaxy scale simulation, maybe finding some observational signatures of black holes that are otherwise hidden. Yeah, to give you an idea of how such a simulation looks like, I show the surface density here, the stellar surface density on the right, the gas surface density here. And you see this very turbulent interplay of cooling, star formation, feedback from individual stellar objects, making these big bubbles. And I think from this you can already see that the black hole has quite a hard time to get some gas in its vicinity. As I said, we are resolving the dynamical friction and the interaction of the black hole with the stars accurately. So that means if we're looking at the trajectory of the black hole, we see that it wobbles around. And in this case, this is actually a physical effect. So we see that the black hole here wobbles around in roughly its sphere of influence, which is 30 parsecs in this case. And we don't have to fix it to the center of the system. Okay, we can now think about experiments that we want to do with the setup. The first experiment that I was looking at was just to place black holes of different masses in the center and to see to which extent they can grow. We are not taking into account black hole feedback at this point. We just want to see how much gas is there that the black hole can in principle consume. And we've done that for 3 different initial black hole masses here, 10 to the 4, 10 to the 5, 10 to the 6 solar masses, and look at the accreted mass as a function of time. And I think what becomes extremely evident here already is that low mass black holes in a dwarf galaxy like the one that I simulate cannot grow at all. So you see the blue curve, for example, after half a gigayear of evolution, it has not even gained 10% of its own mass. It becomes a bit better if you go to higher masses, because then of course the gravitational impact of the black hole on the gas is stronger, but still, even in the case where we do not have black hole feedback, the growth of a black hole is extremely limited. We also see, if we look at the accretion rates, for example, the orange curve here, that the accretion is extremely bursty. So we see periods of time where the black hole accretes, followed by phases of 50, 100 megayears, where stellar feedback shuts down the accretion, because here we don't have black hole feedback again. So the termination of these feedback events comes from feedback from stars. And of accretion episodes comes from the feedback from stars. So this, of course, only gives us an upper boundary on the amount of accreted mass. We already see here we don't accrete much, but we have to think about what's happening if we include feedback, because even though this is not the regime where feedback is traditionally believed to be super important, we know that black holes, accretion disks, they release energy. It needs to couple somehow to the interstellar medium. And we also have some observational evidence, for example, in the great observation by Amy Rines here, where for a dwarf galaxy, it was shown that the feedback from a black hole drives outflows, which have a strong effect on the local star formation rate. So for simulations, that's of course always a problem, because that means we somehow do not just have to worry about how to connect the large scales to the small scales, as we did with the sinc particle accretion prescription. Now we also have to think about how the small scales, which are not resolved in our simulation, affect the large scales. And there are a bunch of different models, of course, possible here. Very typical models are thermal feedback, kinetic feedback. But because we already know that, that there's not much material to be accreted, that it's also worth thinking about prescriptions that are specifically for the regime where the accretion rates are low. For the purpose of this talk, I will present the first two here and the basic assumptions. So in the simplest model that you can think of, and it's used in a lot of cosmological simulations, you can just assume that an accreting black hole releases a certain amount of energy as a function of accreted mass, or a mass accretion rate. And then a certain fraction of this couples back to the interstellar medium, essentially just changing the internal energy of the surrounding, making the particles hotter. In a little bit more sophisticated model, when you try to account for mass outflows, you can assume that a certain fraction of the inflowing mass is launched as a wind with a wind speed that is motivated by observations, and hence drive outflows that have both a kinetic component and a thermal component. Okay, to some of you that might look very similar to the Choi-Ostriker model, but I'm happy to discuss the differences here, because in the way it's implemented, this leads to very different conclusions. Just to give you an idea how these models look like qualitatively, you see that in the thermal case, as expected, you can drive bubbles of hot gas in the center, because we just isotropically heat the interstellar medium. The feedback strength is quite high here. It can drive outflows. This is the plane of the galaxy, and it drives hot outflows perpendicular to it. In the case of the wind feedback, the effect is much weaker, because only a much smaller fraction of the gas is accreted onto the black hole and hence converted into feedback energy, if you want to say it like that. And we see like these wind bubbles, which are much more localized here and just carry a smaller amount of energy. So now we can do the experiment again. In this case, we just fix the initial black hole mass in the center of our simulation and vary the different feedback prescriptions. The blue curve here is what we got in the case where we just ignored the black hole feedback. All the curves down here represent different types of feedback models. And you can see that the feedback in a dwarf galaxy, as we simulated, has a strong impact on the accretion rate. So it comes down by almost 2 orders of magnitude, or the accreted mass comes down by almost 2 orders of magnitude after half a giga-year of evolution, pretty much indicating that as soon as you have black hole feedback, a black hole just doesn't grow in a dwarf. So we can now, of course, try to figure out why that is. And I think the reason why we find that in our simulations is quite well understood. Because if there's no black hole feedback, what's shown here is a very typical situation. So the gas comes close to the black hole, forms a disk, where it cools, then a fraction of this is accreted to the black hole, another fraction is star forming. And in this process, the black hole can consume gas both from the warm phase and the cold phase, where it competes with the star formation. But if we turn on the black hole feedback, the phase where the gas cools down to the temperatures where it also becomes star forming and efficiently accreted. This phase is never reached because the black hole heats the environment before and disperses these clouds before they can cool to the temperatures where they're efficiently accreted. The inflow of cold gas to the center, of course, also has strong implications for the star formation in the center. And we, in fact, find that if we go, for example, to the thermal feedback prescription, the effect of the feedback completely shuts down the star formation in the center. It prevents the cooling of gas there. It pushes out cold gas from the center, such that we cut a hole in the center of our stellar distribution. On the other hand, if we ignore the feedback, we get very centrally concentrated star formation with surface densities which at some point might turn into something like a nuclear star cluster, which Jesse will talk about more later. So feedback is a potential problem for the formation of a nuclear star cluster around the black hole. I'm not saying that the black hole forms first and the star cluster later, but it's definitely something to think about. The interplay of stellar feedback and black hole stellar feedback, black hole feedback, and black hole growth is definitely something that needs better understanding here. Because I'm running out of time, I will just briefly flash some of the X-ray observables that we can infer from our simulation. So essentially what I did was I compared the X-ray luminosities that I got from my simulations to X-ray observations of local dwarf galaxies by Birchall. And what we find is that we actually need the black hole feedback to be consistent with what observations find if we just naively converge the accretion rates into X-ray luminosities. You can see this here, that's the cumulative X-ray distribution. And if we don't have feedback, then too much of these curves lies on the right, so they are brighter than what Birchall et al. Find. If we have the feedback, then we are very well in this regime where we can argue that most of the black holes are actually below the tip of the iceberg, where they are not visible, and we do not exceed the limits, if you want, of these observations. So with this, I just wrap up. So I've presented a model of black holes in a galaxy scale simulation where we can follow the accretion and dynamics, as well as the feedback of the black hole in the context of a resolved interstellar medium. We find that the black holes are not pinned to the center. They wander around quite a bit, which is of course more interesting if we look at this in a merger situation or in a cosmological simulation where we do not start with a black hole that is sitting in the center initially. We find that the accretion is extremely bursty and growth is very limited, giving us good arguments to think that when we observe a black hole in a dwarf galaxy today, that's probably also the mass that it had like a few giga-years ago. Black hole feedback has no impact on the global properties of our galaxy, but in the central region, in the vicinity of the black hole, the feedback changes a lot and has potentially strong implications for the formation or the co-evolution of black holes with a nuclear star cluster. And I think this study is a good starting point to think about more extreme environments, high redshift, merger situations, starburst, where black holes of similar mass might actually grow. And yeah, thank you.
Thank you very much. It was a very nice talk. And I am Tommaso Zana from Sapienza University. And I have a couple of maybe technical questions because I'm very interested in what you're doing because we are also working on something similar. Maybe you can also discuss about details later. Sure. But I wanted to know, given the very high resolution of stellar particles, if you can give me some detail more about the star formation prescription. How do you form it? I mean, in terms mostly of initial mass function. What is the mass of the stars that you form? And did you cap at Eddington the accretion rate of the black hole?
That one I can easily answer because no, we don't. but
Okay.
we never reach Eddington anyways. So
Okay, so go
not
to the
important if you want. Okay. Yeah. And regarding the IMF, we're assuming a group IMF.
Okay, every morning, everyone. And I'm Vittoria Bezzagianolli, third year PhD student at the universities of Roma Tre and Grenoble-Alpes. And today I'm gonna show you some X-ray polarimetric result for the Cipher Galaxy NGC4151 on behalf of the XP collaboration. So thanks to Laura, I don't have to go through this in details, but let me just tell you that it's an ASI collaboration. And in this first X-ray imaging polarimeter in orbit after 40 years, which allowed the X-ray polarimetric study to be carried out for the first time. And so, which is the main aim when study radioquake AGN with XP? Well, this is a schematic view of an AGN with a supermassive black hole at the center, the accretion disk, broadline region, and the torus, and this little cloud here that I will tell you after if it is actually right or not, positioning it here. These are the corona, so it's basically a cloud of hot electron plasma, which through inverse Compton scattering is actually taking the photon from the accretion disk and scattering them and creating the primary X-ray radiation, which is the dominant component in the XP energy band. So, which is the main aim is to actually constrain the geometry of this emitting region. In particular, what we can get from the polarization degree and polarization angle, we can get the symmetry and the orientation of the system. And so how? We have our X-ray emission, it arrives at XP, and XP for each of the detector on board give us these three spectra, which contain the polarization information. And through this formula here, we can get the polarization degree, so the symmetry, and the polarization angle of this X-ray corona. And so, which are the geometry we can imagine for this region? Well, for example, it could be a slab. So the corona in blue is above and below the accretion disk. And then we have the lamppost geometry in which the corona is basically a sphere just right above the supermassive black hole. Or it could be a cone, which in this case, the corona should be like a failed jet. And so, another thing that I would like to point out, since radioquake AGN have a very difficult spectrum due to all the components that we have, it is very, very important to have a broadband analysis. So we need more data from multiple satellites. And in particular, we have the reflection that can actually contribute quite a lot at the high energy band of the XP, the 2 to 8 kV. And this can actually help us to constrain the physical parameters of the corona itself. And so, how about the last 2 years of observation? Well, we have this for radioquake AGN. In particular, we have 3 type 1 and intermediate galaxy and a type 2. For this and this, we only get an upper limit for the polarization in X-ray. Meanwhile, we get a high polarization degree for the Cassinius galaxy, as is a type 2, so the polarization is actually coming from the torus. And, well, then we have NGC4151, which is actually the first radioquake AGN for which we have a constrained detection. So let me present you this source. Is a change in look AGN, is an optical type 1.5 at the high flux state and going to a 1.8, a low flux state. Is one of the brightest AGN in the local universe. And is quite complex in absorption because there are different layers both from neutral and ionized gas. It presented a strong iron K alpha emission line in the past, but in a new observation could actually be modeled with a single Gaussian with width and equivalent with the dark constraint. And as you can see from the different spectra that I put here, Below 2 keV, the soft X-ray emission is dominated by emission line, and the variability of the spectra above 1 kb is quite large. So, the first step of our analysis was to actually consider only the XP data. So we run this P-cube analysis, and we obtain in the whole energy band a 4.9 plus minus 1.1 for the polarization degree, and an 86 plus minus 7 degree for the polarization angle. The detection is actually quite insignificant, above 99.9%. But there are two things that I would like to point out. First is that the polarization angle that we find in X-ray is actually one aligned with the ones that we find in the other wavelengths, and that we have a marginal detection with quite different polarization properties if we divide the total energy band into 3 energy bands. And as you can clearly see from the polar plot right here. And so, second part of the work is actually to consider the NASTAR and XMM data. We model the data with a model implemented it from the one of the literature. And so what we consider. To account for the primary continuum, we model it with a Comptonization continuum, which is illuminating to these two tables that account for the reflection of the emission onto the torus. And then we have 2 neutral partial covering plus a warm absorber for all the different values and layers for the absorption. And then a cloudy table plus a Gaussian to account for some residuals for the softer part of the spectrum. Then the big part of the work, actually put together all the spectra. And so the model is still the same. We just add this pole const, which give us basically the polarization angle and polarization degree of each component it is paired with. And we set to 0 the 2 properties for this table here, which is basically for the fluorescent lines, which they are not intrinsically polarized. And then we set to 0 the one of the cloudy table because it does not contribute into the XP energy band. And so we remain with the one of the continuum, which is the one we are interested in, and the one of the reflection. Here you can see all the spectra, the XMM, NASTAR, and the E spectra from XP, and here the Q and U spectra. Okay, so these are the results by simply applying the model. The polarization is dominated by the reflection, but the reflection in the XP energy band, like the spectral contribution, is only 6%. So there is something going on. We tried a few tests, but still the result didn't change. So another test is actually to fix the value of the polarization degree of the reflection to 15, 20, 30%, which are actually physically motivated values that were found for the Caecilius galaxy, which is dominated by the reflection. And by setting the 2 polarization angle to differ by 90 degrees, we actually found that the polarization degree and polarization angle of the primary continuum are constrained, but the fit is a little bit worse. So what is happening? We think that these results are due to the marginal detection we have in the 2 to 3.5 energy band, which is maybe due to a further component that we were not taking into account at the beginning, which can be some emission, some soft X-ray emission that is actually leaking through all the various layers of absorption. So we actually tried to say, okay, let's try to see if we can decouple this emission from the primary one, because maybe this emission is actually diluting the polarization that we found. And so for each of the 2 partial neutral covers, we set this. So basically this C is just a constant that accounts for the covering part that were detected here, plus a total absorber. And then this little part is actually the emission that we think is leaking. And this actually gives us the opportunity to assign another pole const, and we set to 0 the polarization properties of this emission. And then, again, the polarization is dominated by the reflection. But if we actually set the two polarization angle to differ by 90 degrees, we obtain some polarization properties that are constrained. So this is a comparison of the X-ray polarimetric properties we found versus the ones of the other wavelengths. And we have that polarization angle in X-ray is aligned with the other ones. Meanwhile, the polarization degree is actually way higher. And what it's telling us? It's basically telling us that the reprocessing is happening along the equatorial plane of the AGN. Meanwhile, the emission is happening in different regions, which is actually what we want. And so, last part of the work was to actually say, okay, we have our polarization properties, both from the model-dependent analysis and the model-independent one, which is the geometry that can explain them. So we test a few ones, the spherical lamppost, the slab, and the wedge geometry. The only new one is the wedge geometry, in which basically you have the accretion disk, and when it stops, the corona starts with a certain opening angle, and it acts as an hot accretion flows until ISCO. So we can actually roll out immediately the first one, as the polarization degree that we found is way too high to be explained by it, and the polarization angle expected is the opposite of what we found. So the other two remaining, we actually simulated them considering the Monte Carlo radiative transfer code MONC and cross-checked the result. And these are the results. The polarization angle is actually explained by this geometry, and also the polarization degree. If the actually is better explained by the slab or a wedge geometry with a small opening angle, in which cases the inclination of the source is actually well constrained. It's more constrained. And unfortunately, we don't have the inclination angle of 4151 because it depends a lot of how it is measured. But the results that we obtain are actually in agreement with an intermediate type as 4151 is. And so these are my conclusions. So I would like to point out that the model-dependent analysis and the model-independent one actually give us polarization degree and polarization angle that are in agreement with each other. And the polarization angle that we measure in X-ray is well aligned with the one in the other wavelengths. Meanwhile, the values that we obtain exclude the spherical lamppost. So in the schematic geometry of EGN, in which the corona was above the supermassive black hole, is wrong. Well, it seems to be wrong, at least for 4151. And then, which is the kind of geometry that can have a slab-like or a wedge geometry. And today is a deadline for the XP Group program, and well, let's stay tuned for more and more, hopefully, studies on radio-active EGN and other sources. Thank you.
Thank you.
Thanks for the talk. So can you elaborate a bit why you don't have a good idea on the inclination angle for this source?
Because if you consider the iron K alpha line, it is around 30 degrees. If you consider the broadline reverberation studies is 60 degrees, so it varies a lot. And of course, from these values that we obtain, the angle is actually better if it is higher. So the reverberation is actually those that seems to be actually the value of the inclination. So this could be something to study a little bit more with more data.
And how confident are you on the iron K alpha inclination? I mean, which one of the two you think is more correct, let's say?
I don't know the confidence from the iron K because I was just remembering some literature values. And well, I'm confident more with the one of the broad line, but simply because the polarization value seems to point to that. But that's it.
Okay, thank you.
No problem.
I didn't see all of you.
Is there any chance that the
Okay, thank you very much. So yeah, my name is Jessie. I'm a postdoc at the University of Helsinki, and I'm going to be talking very quickly about nuclear star cluster dynamics. So I'm very grateful that Christian gave us a great introduction to this, so I can hopefully skip over some of the details. So I'm very interested about the formation of nuclear star clusters. We've had some intro about, how they coexist with black holes. But first of all, some sort of motivation. We know that nuclear star clusters exist. They're in the centers of many, many galaxies. This is from a very nice review from Nadine Neumeier from a couple of years ago. And they have this nice characteristic surface brightness profile where you can see the sort of excess in the central part. They're extremely, extremely bright, compact objects. They sometimes host massive black holes or intermediate mass black holes. And they're found in also a wide range of galaxies. And I'm particularly interested in the dwarf galaxy regime. So how these nuclear star clusters actually come to be there is still not understood question. So one of the formation mechanisms is definitely from accretion of globular clusters. There's a very characteristic metallicity and age distribution, which you can tell they definitely have been formed outside of the galaxy and have then somehow come into the centers of galaxies. That's not something that I look into. You need a cosmological context for this for sure. I'm more interested in looking at the in situ formation, which we also know occurs. How does gas and stars actually end up in the center of galaxies to form nuclear star clusters? So again, I can skip over the details of this. Thankfully, this has already been introduced by Christian in the earlier talk. I used the Griffin model, so this is extremely high resolution simulations with complete star formation model as has been described. And I'm showing here a minor merger simulation, so this is slightly different than what's been shown. The central main galaxy has a baryonic mass of 6 × 10⁷ solar masses, so this is really a dwarf galaxy. And then the small galaxy that we threw at it was a tenth of that mass, so it's a 10⁻1 merger, with the idea that, how can we channel gas to the center? So we're looking, for example, in this merger scenario such that we form a nice starburst and trigger some radial inflows. So this is kind of one of the results. You can see the stellar distribution on the right, and here you can see, the surface density similar to the surface brightness profiles I showed before, and you can see this really nice excess in the center of the new stars. This pink line here shows you the new stars, and you can see we really have an excess of stars in the center. But you might notice, I don't know how clear it is, on the right-hand side, we see that there is an excess of stars in the center, certainly, but it's kind of a cluster of clusters. There's some missing dynamics, which I'm going to quickly address. But we managed to get stars to the center, so we know kind of the fuel of star formation. We can get these merger-triggered inflows, and we can start to look also at star cluster formation as well. So I looked in a paper from last year at star clusters in the outskirts of the galaxies. Of course, star clusters can come together and can form nuclear star clusters, so we start to look at that. That's what I show in the right-hand plot there. I'm tracking star clusters over time, tracking their feedback events. In the background of this image, I'm showing the outflows. This is something else we try to understand, outflows driven by clustered feedback. But we can trace the clusters through time and try to see what happens to them as we evolve them over several hundred mega years. And then the final piece of the picture that I'd like to look at eventually is also the interaction of nuclear star clusters with a central black hole. So stellar and black hole feedback, we've already had this discussed, but also how do nuclear star clusters actually evolve with black holes? And for that, we use something that was introduced also by Anti's talk earlier, which is KETU. So a brief kind of introduction to what KETU actually does. We have this regularized region around a black hole. It doesn't actually have to be around a black hole, so we can evolve star clusters without black holes. But we can look at the black hole and stellar interactions, which I've drawn with the blue arrows there, and we can also make this kind of an n-body region, so we can also have unsoftened stellar interactions. And I think this is really the key to be able to understand nuclear star cluster formation. At the moment, we kind of get very, very clustered star formation, but we don't really capture the disruption and maybe the merging of the star clusters. So this tool, in addition, which is coupled with the simulations I mentioned earlier, this tool is really probably going to be the answer to understanding nuclear star cluster dynamics in these hydrodynamical simulations. So complete picture of star formation with gas in a hydrodynamical full galactic setting with this resolved dynamics in the very center. So I leave my summary slide here. We have formation of nuclear star clusters we know we can get now with this merger setup. this very nice central concentration of gas and then stars, we can track the star clusters through time and understand the effect of their feedback, and also understanding how they could potentially merge to become nuclear star clusters. And then we can add in this extra tool, which is to really understand the dynamical evolution of star clusters and nuclear star clusters to help us understand how they come to be and try to understand some of the observations. Okay, thank you.
So we've been informed we have some time for questions now. So if someone has a spot-on question for the speaker, please feel free to make it now.
So, hi everybody, I'm really excited to be here. This is the first time I'm visiting YAGN. I'm from the University of Vienna, where I'm doing a master's. And as you can see from the title slide, I would like to take you through my project, which is the measurement of the central black hole mass in NGC 2513, which is a massive elliptical galaxy. And I'm using ALMA data and the method of cold molecular gas dynamics. So a little bit of data about the galaxy that you can take away is that it's massive. It's also brightest group galaxy, and we have a relatively high velocity dispersion, which is important for the method. We'll see why. And from a rough estimate, we expect a massive black hole in the region of high 10 to the 8 solar masses, perhaps even a 10 to the 9. So let's talk about the motivation. I think we've actually heard quite a lot today about AGN feedback and such, and so we know that the supermassive black hole has very likely a co-evolution with the host galaxy, and this is something we'd like to explore. We also had some really interesting talk from Federica, but coming from the dynamical method, which is very active, and especially the method that I'm using, we're hoping to add to the database where we can add to robust black hole mass measurements. And what's really exciting about this galaxy is there's no previous black hole mass measurements, so we'd like to add to the database with this, and hopefully I'll get a good result. So dynamical methods, in principle, we have a tracer. This can be, as you know from our own galaxy, we can take the proper motion of stars, or otherwise in other galaxies, stellar dynamics. We can use ionized gas, masers. But a relatively recent newcomer to this method is the cold molecular gas dynamics. And why cold molecular gas dynamics? Well, it's dynamically cold, and this is quite important because we have then the gas, the tracer, reacting mainly to the potential of the black hole. It's not really influenced by magnetic fields or radiation fields as ionized gas would be. It can work for quiescent black holes, it works with AGN, so it really has a wide range, and most importantly we can apply it to many galaxy types. In fact, black hole mass measurements have been made to all Hubble types of galaxy. And there's a predicted range of about up to 100 megaparsecs. So what's really important is that the tracer should be in the vicinity of the black hole, and what you can see here, or not, is sort of a field of view of 3.17, and I'm going to show you now the ALMA footprint. So that's the data that we get within this footprint. But to give you more of an idea, if I zoom in, we're looking at a really tiny part of the galaxy. So this is zoomed in. It's a bit of a back of the envelope sketch here. We really need to get close in. And we've heard a little bit about the radius of the sphere of infants today. We estimate for my galaxy the 0.22 arc seconds, which I can tell you how I got that. And luckily for us, we have high-res data from ALBA, which has a radius of about 0.15, so we can resolve that sphere of influence, which is good news. The basic idea behind the dynamical models is to look at the total masses and accumulation of the black hole mass, the luminosity, and dark matter, and then rearranging that equation, we get what we see here. And first of all, let's take a look at the luminous mass. So of course, this is an important thing to model. So this is actually one of my first results, which I'm happy to show you. But basically, we're using data which is usually from the HST. It's important that it's high resolution. In my case, I only had one image. There's only one filter being used, which is what you can see here. And what we do is we model the 2D surface brightness using multi-Gaussian expansion, the MGE method, which you can read about for details in Capillary 2002. And from this, we can retrieve 3D intrinsic luminosity density. So, of course, as you can imagine, it's important to do a bit of masking. So we have stars that are masked, and very importantly, the dust in the center. So dust is quite ubiquitous where we have molecular gas, and I don't know if you can see it, but there's the dust in the center. You can see the pixels are slightly darker. So it's really crucial to get an accurate luminosity model. Otherwise, the supermassive black hole mass itself will be affected. And then we get our mass density simply from multiplication with the mass to light ratio, which is a free parameter in the dynamical model. And I'll take you through that in the next slide. So unfortunately, I don't have my own results yet, so I'm busy working on those, but I can show you some results from Davis et al. 2017. But the main idea is to generate from the ALMA cube that you have. You get a cube of data, sort of RA and declination and velocity. And with that, you can, for visualization, make a kinematical map. So this is the first moment velocity map, and you can clearly see there's a nice kinematical axis there. And using the cube, you put this into your model, which is produced by the kinematics with KineMS, kinematic molecular simulation. This is by Davis et al. And it's specifically for cold molecular gas. So putting that in with various parameters, the black hole mass being one of them and the mass to light ratio, you're able to generate models, and that you can see on the right. So not only does KineMS, of course, generate models, which allows us to compare with our data, using MCMC, we get then a best fit, and this actually is the best fit from Davis. And you can see that it actually reflects quite well. And what this best fit does is give you the best fitting supermassive black hole mass. This is also quite clearly visible here. I don't know how familiar you are with position velocity diagrams, but this is basically taking the kinematic axis, you take a slice along that and rotate it, so you have the velocity here and the position. And I usually ask students when I give this presentation back home, what do you think the best fit is? So on the left here you can see a scenario with no black hole mass, and on the right with a very high black hole mass. And here, for instance, you can see the data, which is the orange, does not really match the fit of the model. And here as well, the model is far too low. But the peak in velocities, this actually shows the peak of velocity generated by the excess mass in the center, fits very nicely, and that gives us the best black hole mass. So that brings me to my conclusions, which is basically the importance of robust data set, the many advantages that cold gas dynamics gives us, and what we use to get those measurements. So thank you very much.
Thanks to you. And if you have any questions, please raise your hand.
Thank you. So, sorry if I missed it, but what is like your sample size up to now of masses with ALMA dynamical measurements?
So yeah, that's a really good question. So I actually did my bachelor thesis, and that was about 3 years ago, 2 years ago, and it's actually a
the host galaxy properties of changing look AGN. And just sort of briefly for anyone who doesn't know, a changing look AGN is switching between a Seyfert type 1 and type 2, or gaining or losing those broad or narrow emission lines on month-to-year timescales, so very, very rapidly. And they seem to be situated in slightly different host galaxies than your typical AGN, which are found in star-forming galaxies. These changing look AGN are primarily in galaxies that are falling off of that star formation main sequence. So they're shutting down star formation. Why? We don't know. We don't understand why changing look AGN are in such a different host galaxy population. And we want to understand why that's happening and whether something that's physically triggering that end of star formation might also be triggering the changing look behavior. So what I want to understand is what are the star formation histories of these host galaxies, because if something's quenching them, it might also be triggering that behavior, and by understanding that star formation history, hopefully we can get a better sense of what that physical mechanism might be. I'm using Prospector, which is a Bayesian galaxy SED fitting code. I'm happy to talk about that a bit later. But essentially, we're trying to get out a star formation history, and in particular, we don't want to force that star formation history to conform to a specific shape. We want to understand how that shape is different from typical AGN. But as some of you might imagine, that contamination from the AGN can really impact our star formation history fits. In particular, it can make a galaxy look like it's forming more stars at the present than it currently actually is. And so we need to test to make sure this is actually feasible before we go in with our non-parametric fits. So we start off just trying to determine whether we can actually recover whether galaxies are star forming or quiescent with a delayed tau star formation history model. And as you can see, we get a pretty neat separation between quiescent and star forming galaxies. This is just a little pilot study we did with some galaxies where we had a very narrow line emission spectrum in SDSS, just as a proof of concept. And those classifications are based on the location of the host galaxy in a GR color magnitude diagram. So great, we can do it. So we start to do some non-parametric fits. We're using a post-starburst model made by Ren Seiss. This model is really great because it allows for flexibility in the size of the time bins at later times in the universe's history. But it doesn't enforce a starburst, which is what we want. We want to understand if there was a starburst, but we don't want to see starbursts where there weren't any. And in our sort of initial fits, we are seeing that we get a difference between the star-forming and quiescent non-parametric fits. The quiescent galaxies tend to have had no star formation in the last gigayear or very little. The star-forming galaxies are continuing to form stars within the last gigayear. So that's great. Awesome, this might actually work. We are getting a little bit of weirdness for some of our galaxies. We've been seeing this feature, this almost vertical star formation feature at recent times. And we think that that might be due in part to contamination from the AGN. We see that feature is more severe in galaxies where we are fitting with the broad line spectrum rather than the narrow line spectrum. Luckily for a lot of these galaxies, the narrow line spectrum is available publicly through SDSS, but it's not available for all of them. So I'm currently in the process of reaching out to people who have that data and asking them to please give it to me. In the future, we hope to constrain these star formation histories for all of the non-quasar changing look AGN hosts that we've found so far. There's about 200 total within a redshift of about 1. And then we can do some population statistics. We can ask how are these star formation histories different from the star formation histories of more typical AGN hosts. And in particular, we can ask what quenching mechanisms are happening here, how are these galaxies falling off the star forming main sequence, and what does that tell us about what's physically causing that changing look behavior. Thank you.
Thank you very much. And please, oh, thank you.
Thanks for the talk. Can you please elaborate a little bit more on what are the additional information that you're using to constrain the contribution of the AGN on the optical line?
Yeah, so when we run our actual fits, we are, first of all, just masking out any emission
continue with low redshifts, nuclear dynamics and transients as we did in the morning session. So we have more talks about this topic. So the rules stay the same, 15 minutes, then 10 minutes of questions. I will show 5-minute and 2-minute marks. And as a first speaker, we have Marzena Sniegovska from Tel Aviv, Israel. Please go.
So, hello everyone. I am a postdoc at Tel Aviv University, but I will be talking still about my work, which I've done in Warsaw, in Poland. Yeah, title is a bit long, but let's go through it together. So I will be talking about modified models of radiation pressure instability. So first I will, that's not what I did. I need help. Okay, so in the meantime I will tell you. So I will explain you what are changing look, but we already had a nice introduction. I will explain what is this radiation pressure instability and then what actually we modified there. Yes, so I think we are all familiar with this picture already, and I want to stress out just that, yeah, we say that the broad lines are produced in broad line region and narrow lines in narrow line region. And here you can see optical spectrum of Markarian, with some number, and here we can see the spectrum of the same, is the same source, just they were done in different times, and you can see H beta and oxygen 3. H beta is quite important line because it's used, for example, to estimate black hole mass. Yes, so it's a bit problematic when it's not here, or then it appears, then it disappears within tens of years. And we know that it cannot be that the inclination of the source changes. We don't change our position, the source, not in this time scale, of course, yes? So what's going on there? Yes, so that's the first point. What's going on there? So changing look are quite interesting to understand what's going on. Then we can also think about host galaxies, which was already mentioned. And when we try to model them, we are improving our knowledge about AGN physics in general. So I grouped possible scenarios, because I will be talking mostly about the theory. So yes, possible scenarios I grouped into 2 classes, extrinsic and intrinsic one. So we can have some variation of obscuration, maybe some tidal disruption event, and in general, changes in accretion rate. So now we will slowly go through all of them, and I will explain a bit problems which we have with all of them. So variation of obscuration, it means that we may have some clouds in our, line of sight, which somehow covered this broad component of the line. But then we have also some counter-arguments, because how big should be this cloud? Where should it be? There were studies of low level of optical polarization in changing look AGN, which suggests that probably there is no clouds in these particular ones. And then also, like, multi-band recovery, which we notice, is also quite inconsistent with obscuration. But I know that there were some sources for which the obscuration is the most possible one. Then we have tidal disruption events, and the problem with them is, like, first of all, spectra, yeah? The spectra, like, we don't have the particular line which we see in traditional TDEs, also the time scales. But in some, maybe the answer could be provided by tidal disruption events. But when we have repetitive changing look events, it's getting, again, a bit tricky. And then we have the most exciting for me, changing in accretion rate, whatever those changes means. And then the question is, what exactly would be those changes? What would start the process of instability? And this instability, it can be radiation pressure, it can be ionization, maybe something magnetic. what kind of timescales we will get from all of them. And probably, if we are using standard Shakura-Sunyaev, we will probably need some extra things to shrink the timescales. So I will start with some going through literature. That was, I think, the first proposed model of what could explain the changes in Markarian 1018. So on the right side, you see spectrum, the archival one from SDSS, quite old one, and newer one from FORCE and MUSE instrument. And you can see that the broad component of H beta disappeared. Also H alpha changed. And the proposition is by Noda and Dan that it can be some kind of ionization instability. And we have something which is called ADAF, which is advection dominated accretion flow, this yellow thing, which is in hard X-ray. And then we have something which is called soft access. So this is this part of X-ray spectrum. And also you can see that this thing also changed within the years. So it suggests that this soft access could evaporate into ADAF. So this works for Markarian 1018, but there is another source for which also we noticed the change in with broad component, but there was no warm corona, because this soft access is said in the literature that it can be caused by warm corona presence. So what we know now, like we have few sources and probably not just one mechanism. Yeah, because for Markarian it works, for the other, not really. There is another source, research done by Nick Ross, and they proposed some cooling front, on which I will explain in a while. And maybe let's take first a look to spectra. We see this blue, which is archival one. Then we have a spectrum from BOSS, red one. And you can see that here it dropped dramatically in UV. And then it came back to as it was. And then the question is like, what could have happened? And they proposed that it could have been some cooling front, which went through accretion disk. That's why it caused this dimming here. And then it came back to heat the matter and ionize it again. So it came back to as it was. And it could have been maybe by some changes in magnetic field configuration. There was no calculation, it was just a proposed scenario. But again, we have one source and one model. And now I will tell you about the model which we've proposed with a group from Warsaw. And for now we have two sources. So it's one model and two sources. So we did a bit better, okay? Then so we used something which, we used the Shakura-Sunyaev disk model, and I will start from something which is called S-curve, because it will maybe explain the computations we've done. So this is the plane which is like a surface density and accretion rate. It can be also temperature here, because they are proportional. And if we are solving those stationary solutions using all of those equations, and I don't want to bother you and myself with numbers, so I just stressed what was used in this model. And we are assuming those differential equations to be zero, and then we are getting this kind of S-curve. And we are getting those positive slope one are stable solutions. So here we have advection dominated solution, gas pressure dominated, and radiation pressure dominated one are with negative slope, which means that this is unstable solution. So this thing could cause some maybe outbursts if we try to model it with time dependence. So here we have our stationary solution, and I will show you how it looks. It's a bit engine-like. No, like this. And we have like 3 phases. First, we have the phases where mostly surface density is growing. Yeah, is this red part. Then we have this black part, which is a heating phase when the temperature grows, and then the cooling phase till it meets this gas pressure dominator. This is for 10 solar masses because it was easier to compute for 10 solar, but it will look, the shape, it will be the same for any black hole mass you have. Yes, and we decided to do actually 2 papers about it. First one was a very like a toy model in which we assumed very narrow unstable zone in the disk. So we have black hole mass, ADAF, this unstable zone, which we computed, and then outer stable disk. And we followed time-dependent evolution of just this blue part. And we assume that our timescales, which we are getting from Shakura-Sunyaev assumption, are shrinked with the size of this unstable disk. So then it's quite easy to regulate the timescale. And we just focus on timescale. We didn't compute any spectra, we just focused to get the timescale. And here are our results. And you can see that this model is extremely sensitive to whatever we adopt. If we adopt different M naught, it looks different. And shape does not look, I will show you observation in a while, like with shape we are far from what we observe in AGN, but we are not the only one who have problem with this. Yes, and this zone structure may be, of course, easily affected by any local phenomena we have around, but we can get, we were focusing of getting around 10 years. That's the time scales we were looking for, and those are the data. So, yes, the up we have NGC 1566, and below we have our friend on which Vittoria already was talking, but from X-ray perspective. And here we have photometry and some outbursts. So we decided to match the time scales. We did match, but we wanted to get something more. Maybe I will walk you through the plot on the right. So we have m dot, which is relative accretion rate. Then we have alpha, which is parameter from Shakura-Sunyaev. This is viscous parameter. And then this delta R is how broad it was this zone, this unstable zone we had. Yes, but I said we were a bit hungry for more things. So we decided to try a bit more complex solution. We added corona, which was like this sandwich-like, and this unstable disk now is not just one box, but it's a grid. So it's a bit more realistic, yeah? And if we compute this unstable disk as we should, like for the whole, if you assume it like quite big as the accretion disk could be, then we have problems with timescales, yes, because we don't have, we don't want 1,000 years, we want like around tens. So then if we reduced this outer radius of unstable disk, we obtain tens. So again, we did a bit of the same trick, we just shrink this unstable zone. So we decided to test using this code written by Agnieszka Janiuk, and we modeled the luminosity changes, and I will focus only on this 10 to 7. We added some extra things because just by modeling it, we were not able to get the time scales. Here we have exemplary light curves, and here the time span is 200 years, and the gray one is accretion disk light curve, and the red one is corona. So we can see that corona is just passively following whatever is happening with accretion disk, and this upper panel is about adding some extra component from presence of magnetic field because we needed it to shrink, or as I said, like really harshly, we were cutting the outer radius, and once we were cutting it, the time scale shrink. Here we were again getting around 10 years. And here just some example of light curves with small outer radius, because I was just trying to see how much we can shrink this 10 to 7 black hole mass, and what is the smallest time scales we can get. And we can get around 1 year, a bit less. And how to explain this outer radius? Yeah, we thought that maybe it can be some leftover from tidal disruption event, or maybe we have some smaller black hole, stellar black hole mass, which is just traveling around and making this gap. But we don't have any boundary condition yet to this. But it will be done. That's on my to-do list. I will leave you with summary, and thank you.
it's time to move. So next one in this session is Martin Vaughan from University of Cambridge, UK, who is going to talk about simulating black hole accretion, spin, and jets. Please go ahead.
Okay, yeah, first thank you for letting me come and present these results. My original title was Recent Progress in Simulating These Things, until I realized that this bunch of people have been working on this stuff for quite a while now, so I shortened it slightly. But I'm going to try and give you an overview of a few different topics, all related to how we simulate supermassive black holes and various processes involved there. So this is a slide I probably don't need with this audience, but why we need supermassive black holes? Well, if we look at large-scale cosmological simulations that try and capture, the evolution of a population of galaxies, AGN feedback is often argued to be necessary to give us the correct shape of the stellar mass function at high masses, regulating the star formation or quenching star formation in this region, plays a role in regulating black hole growth and normalizing the scaling relations. A multitude of cosmological simulations found that adding AGN feedback meant that you could produce realistic galaxy populations, and by that I mean not just having large star-forming disk galaxies, but also getting quiescent elliptical galaxies as well. There are other things, AGN outflows expected to help enrich the CGM, pushing metals out to very large radii. They also regulate the thermodynamic state in groups and clusters. And I'll talk a bit about that later on. But in general, I think we can boil all of the stuff related to supermassive black holes down to three questions that seem quite simple and compact when you look at them, but underneath there's a whole range of things going on, as we've already been hearing about. And so we can think about how and when the supermassive black holes form, how do they grow. This, in my mind, includes handling the black hole dynamics, the mergers, and the accretion. And then how do they impact their environments? And again, this is through feedback, but also through their dynamic interaction with other things in the system. But the problem when it comes to simulating these things is the dynamic range challenge, right? So if we're interested in the black hole, the accretion disk, the process is producing, say, your jet or your winds. We're on very small scales, a few gravitational radii and beyond. But if we want to self-consistently capture the environments that these black holes form in, and that they grow in, and that they interact with and have an impact on, you want some sort of cosmological environment that captures hierarchical structure formation over the age of the universe to set up your environment. But capturing all of this isn't possible, nowhere near possible in individual simulations, and so we have to make various assumptions and simplifications. And this is, I guess, the work that we'll be doing is trying to come up with ways of bridging gaps and capturing more physics within the simulations that we perform. So all of the simulations I'm going to talk about were performed using a repo. This is a hydrodynamics code, or also magnetohydrodynamics code. Can be run for cosmological simulations as well. But the main thing I just want to highlight is that the hydrodynamics is solved on a moving Voronoi mesh. And one of the nice things with this mesh is that you can either refine, so split cells and improve your resolution, or de-refine based on fairly arbitrary criteria. And traditionally this is done to maintain cell mass, but you can do other things as well. And so, for example, one of the key models that a lot of the work we've been doing now relies on is a black hole refinement scheme, or a super Lagrangian refinement scheme that was developed by Mike Curtis 8 years ago now. He was a former PhD student in our group, where essentially if you have a black hole in the center of your simulation, you have some refinement region, and you can progressively improve the spatial resolution within the simulation as you get close to the black hole. And the original aim of this was to make sure that you could resolve Bondi radius within the simulation. But running simulations with this, for example, high redshift, massive quasars, it was found that if you compare a run with this high resolution around the black hole to one without this, and just using a simple thermal injection of energy, you can end up with very different morphologies, for example, for the feedback that you get, where you get this bipolar outflow instead, and a cold disk forms around the central region. This is just a slice. And then we've used this model in a number of other works as well for a range of reasons. And then another model that is quite important for the work that we've been doing, and in some of the stuff that other stuff I'm going to talk about, is to help us model accretion. And this is work done by Davide Fiacconi, who I think a number of people here know, who's unfortunately left astronomy now. But he developed a model whereby you have your black hole particle in your simulation, but what's going on below the resolution limit is that this is capturing both a black hole and a Shakura-Sunyaev accretion disk, and this model tracks both the masses of these objects and their angular momentum, or the black hole spin. The assumption here is that you have this Shakura-Sunyaev accretion disk, you have a warped disk, whereby the Bardeen-Peterson effect can lead to torquing between the black hole and the accretion disk, and so the model can track both the evolution of the magnitude and the orientation of the black hole spin. And then this model is fed from the resolved regime through mass and angular momentum inflows. And this is just an example of the spin and the accretion disk angular momentum vector in various environments where you have some sort of coherent accretion, a coherent gas distribution, or a more turbulent gas distribution from the original work that Davide did. So taking these two models, something that we'll be doing recently is using these to do binaries, black hole binaries in gas-rich circum binary disks. Firstly, using the refinement scheme, the black hole refinement scheme, means we can get high resolution within the cavity and capture the streams and the mini disks around each black hole, which play an important role in torquing the black hole and affecting the evolution of the binary properties, and in this case, helping to shrink the binary. We've performed a range of different binary setups, so circular, eccentric runs, binaries in which the binary is misaligned by 45 degrees to the circumbinary disk, and also a couple of retrograde binaries as well for mass ratios of 1, 1 to 3, and 1 to 10. And as is often done in these simulations, we've looked at the gravitational torques, and similar to other recent works for the prograde cases, we find that you get these positive torques from gas within the vicinity, or net positive torques from gas within the vicinity of the binary, and net negative torques at larger radii. And in these simulations, the torques that we're finding are always negative, so acting to shrink the binary. One important fact I've just realized I didn't say. So for these binaries, we include self-gravity, and we use an adiabatic equation of state with beta cooling. So these aren't using an isothermal equation of state that's often assumed either. And then, in the retrograde case, we find that the gravitational torquing is dominated again by material close to the binary, but in this case, because of the opposite orientation of the angular momentum, these torques are now negative and acting to shrink the binary as well. And then one of the other things we can do, because we're including this subgrid accretion disk model that tracks the spin, is we can look at how the black hole spins evolve within these binaries. This is interesting because whether the black holes are aligned, the spin of the black holes is aligned or not, by the time they come to merge, it can impact, for example, the recoil velocities that the remnant has, which then, if the spins are sufficiently misaligned, you can have high recoil velocities that eject the remnant from the host, and this then lowers the occupation fraction and reduces the gravitational wave detection rate. So these alignment timescales are the alignment timescale for the spin to align with the accretion disk angular momentum. We can compare it to an analytic model from Droser 2015. In all cases, even for the primary black hole in low mass ratio systems, we get alignment timescales that are either close to or shorter than the in-spiral time. So we'd expect spin alignment, at least for the spin in the subgrid accretion disk. One thing that does come up is that for our misaligned binaries, we can see that things get a bit messier, and in particular, the mini disks that form around the components in the lower mass systems, their orientation can vary quite a lot, and they take a long time to align, which means the accretion flow onto the black hole and the alignment of the black hole spins with each other isn't necessarily guaranteed, at least for the timescale of the simulations that we've seen. Just sort of to illustrate this, this is more of an artist-style volume rendering. But anyway, you get the idea here that this mini disk is not aligned with the larger scale accretion flow from this warped circumbinary disk that we've simulated. Okay, I think I need to speed up a little bit. So something else we've done is looking at jet feedback in galaxy clusters using this model. So an open question here is how the jets actually heat the ICM, and there's a whole range of different processes that I list up here. But essentially, using the superlagrangian refinement technique and allowing the resolution to go with the jet means that we can capture the jet itself a very high resolution and get high density contrast between the jet and the ambient medium. We've then used this model to study fixed power jets within a cosmologically evolved low redshift galaxy cluster. This is just a large scale view of this, to look at how the jets interact with the cluster weather and how they heat the environment, how they communicate their energy. This is just an example of what's going on. So instead of the standard picture where you inflate lobes that just buoyantly rise through the ICM, we have a bulk motion that pushes the top lobe and jet material across. We have some substructure here that's interacting with this southern lobe as well. And this all has an impact on lobe lifetimes and mixing. This is just another illustration of it. This is just a few examples of some mock X-ray images we made, mock radio images showing the different morphologies and the radio lobe structure, the X-ray cavities that we see. We've also looked at the energetics, how much energy is in the lobe, how much goes to the environment. We generally find about half of the energy remains in the lobe during inflation, half is communicated to the environment through the work done and in driving shocks and moving material around. This is fairly consistent with the lobes inflating in pressure equilibrium for the majority of the inflation phase. One of the interesting, or a couple of things to point out, is that the lower power jets are more susceptible to this weather-aided mixing, and that's the primary way they communicate their energy to the environment, while the higher power jets drive more and stronger shocks and directly heat the ICM through this shock action as they're inflated. Those simulations didn't include magnetic fields though, so this is stuff that we're literally starting to analyze at the moment, comparing runs where we have magnetic fields within the cluster or not. And you can see that in the case when you have the magnetic fields, you can suppress the formation of the instabilities. And if we look at this quantitatively, this ends up reducing the level of mixing and prolonging the lifetime of the lobes when we do have the magnetic fields. And then bringing all of that together, work by Rosie Talbot, who was our previous PhD student, coupled the jet feedback model to the subgrid accretion disk model, and combine these by defining the efficiency for the jet power and the jet direction based on the spin, assuming a Blanford-Nyack process, getting this efficiency from GRMHD simulations. Here's just a couple of examples. This is just a jet directed immediately along this way. This jet, or this black hole spin, and hence jet, was initially fired into the circumnuclear disk and drives this multi-phase outflow. There's a few more examples here. Instead of what you normally traditionally expect for jet feedback. And you can see that the spin direction is evolving and moving up here as the black hole gets torqued by accretion from material in the circumnuclear disk. And then more recently, Rosie has done idealized simulations of a gas-rich disk galaxy merger, including the secretion model and jets, looking at the star formation rate, the formation of cold gas in the outflows. And one of the interesting things in this case is that the cold gas that forms in the outflow can end up falling back towards the black hole, and in this case then ends up talking the black hole back towards the plane of the disk. And then I think the last thing to just flash up is some work from Sophie Kudmani, who has been developing the subgrid accretionist model further, such that it can capture both a thin disk, a truncated disk, and an ADAF disk as well, or ADAF regime, should I say, depending on the properties of the accretion flow. And then we've also been coupling this with a new wind model that is very similar to the jet model I introduced earlier, but now we have a wide-angled outflow, again with the refinement scheme, so we can have this high-resolution wind feedback as well that's being tested in a few different environments. And I think I'll stop there and leave my conclusions. That's fine.
So, questions, please. Okay, we'll start here.
Thank you. A nice talk. Apologies if I missed it. Maybe you mentioned it. But can you compare, like, with your simulation, what you expect for like Berzan type relations? You know, the ones between the kinetic luminosity and the radioluminosity for your type of sources. So, you know, compare with the observational types, because you know there are like several different relations out there, and maybe you can say what is the best.
So I think in terms of the kinetic luminosity and the radioluminosity, I'm not sure how well we can do that with the simulations we've done so far. In particular, the early ones where we don't have magnetic fields included, we're essentially just painting them on to get the synchrotron, which gives you the radio. So yeah, I think we need an improved model in terms of the magnetic fields within the jet for that. The other common relation that you get with these lobes is obviously looking at the PV quantity of the lobe versus the cooling within the cluster. So one thing we have done is compared the what is essentially the instantaneous PV. So if I take pressure from the environment and the volume of the lobe, and if I compare that to the integrated PV, because we've simulated, we can integrate PV as the lobe inflates, and yeah, quite often the instantaneous PV will underestimate the integrated thing, and this is because initially your jets are overpressured, and so this contributes to the overthink. So that means that you can then underestimate how much energy you're actually injecting into the system.
So the next speaker is Luca Procci from Milano, who is going to tell us about rates of TDEs and MREs in galactic nuclei. Please.
Okay, so hi everyone, I'm Luca, and as you have seen, I work in Milano. I'm finishing my PhD there, and I'm working with Alberto, Massimo, and recently we are moving to the dynamics of these tidal disruptions, and so I'm working with Nick, Elisa, Matteo. Davide is a master student who contributed with some of the plots you will see here. So I will give you an overview of what happens in nuclear clusters and how we can model the dynamics to get the rates of tidal disruption events, MREs and plunges we expect. So first of all, nuclear clusters. You have an if you look at a particle there, it will move on an orbit. This orbit is mainly determined by initial conditions and the potential of the system. So you have both a central black hole, which is dominating in the inner regions, and the stellar distribution. So it will also contribute to black holes. Moreover, these environments are very crowded, which means it's not unlikely that a star will cross another star inside these clusters. So you have two stars on their orbit, they meet, they interact for a bit, and they alter each other's orbits. So this will lead to variations in the orbital parameters of each star, and it is possible, as Elisa introduced us this morning, that some of these particles will end up in deadly orbits. If you're looking at an extended object, as we've seen today, you can go through a partial or total tidal disruption event. So the pericenter is so small that tidal forces disrupt your internal structure. Otherwise, if you're considering a compact object like a stellar black hole or a neutron star, it is possible that we think that the structure survives tidal forces so that the particle can get so close to the central black hole that gravitational waves emission will start dominating the evolution, and eventually you will have the coalescence with the central black hole. So you can look at this picture like playing around with nuclear clusters. You could do it in principle with an n-body integrator, look at a system. Historically, you can also do it by looking at the average, the expectation value of the kicks you model inside this system. So you track a particle. Imagine you are considering the orange part. Sorry, the pointer is this one. So looking at the upper panel, you have a particle that starts maybe here. It interacts with other stars. It receives random kicks. And initially, they change a lot, both its semi-major axis on the vertical axis and the eccentricity. On the horizontal axis, we have 1 minus eccentricity. However, at some point, the kicks will put your star on an eccentric orbit, so eccentric that interactions with other objects will mainly alter the eccentricity, freezing the energy and the semi-major axis. So you will start moving horizontally here, and you will maybe be driven inside this light blue area called the loss cone, which is the area of pericenter corresponding to pericenters so small that you will have the deadly event. If you have a compact object, then it is possible that your star starts its evolution or is eventually put by other stochastic interactions so close to the central region that stochastic interactions are inefficient when compared to gravitational waves emission. So the evolution will start to be more and more dominated by the deterministic effects of GR, and you will have the MRE phase, so extreme mass ratio in spiral. This is called extreme mass ratio in spiral because the stellar black hole has a mass which is much, much smaller than the central black hole, let's say 1,000 or less. And this happens if you can withstand tidal forces. If you cannot, both of these orbits will actually end up, at least for central black holes below 10 to the 8 solar masses, at a larger pericenter, so that even these orbits will end up being tidal disruption events. So this is classical results of loss cone theory. as Elisa mentioned today. In 2022, we wrote a code to solve the mean field evolution of a nuclear cluster due to these effects. If you model it, you get a Fokker-Planck equation in energy and angular momentum. You set your initial distribution, you let the system evolve. Scatterings will alter your distribution function, that is the distribution in this space, and eventually you can track at each time what is the rate of particles entering the loss cone, namely doing a partial tidal disruption event, an emery, or a plunge in time. So with such a code, you can study in principle many parameters of your evolution, like the total number of tidal disruption events, emeries, direct plunges. You can study the stochastic evolution of the system, so you can ask what is the final slope of the distribution of stars there. And actually, we did it in a paper. So in this paper I'm referring to, we took some typical nuclear clusters, like we took the mass of the central object, we took the mass sigma, associated it to the velocity dispersion to a stellar distribution. We scaled the total number of objects with the mass of the central black hole, and then moved around the mass sigma relation. So we changed the mass of the central black hole, we changed the velocity dispersion, and we also changed the inner slope of the distribution. So we put them on a Denon profile, so outside is fixed, inside you can change it. So you run many simulations, and what you find is beautiful. This is numerics, purely numerics. All of our simulations seems to be related one to each other by rescaling the rates if you track them in time. This is amazing because as soon as you realize that, you say, wow, my results can be parameterized by a very small number of parameters. And indeed, this is why we get scaling relations. Keep in mind that we set the initial conditions, scaling everything together. So this is not completely a surprise. So what we found is, for example, that if you track in time the total number of emeries, tidal disruption events, they are proportional one to each other, and they are roughly linear with the mass of the central black hole. We find that for each emery, you have 14 direct plunges, so direct captures without the long gravitational wave dominated phase, and roughly 3,000 tidal disruption events, with no dependence on sigma, which seems to alter only the relaxation timescales, which means the time over which you do all of these events. So we tried to translate all of these captures into a mass gain of the central object, because 3,000 stars, like for each black hole, can be relevant for the mass growth. So we asked, what if we take the average rate over our simulation and we translate in the time to double the mass of the central black hole? Then you get an estimate of the time of growth of the massive black hole. And what we see is that for systems on the mass sigma relation with a central black hole smaller than 10 to the 6 will likely double their mass, according to our results, in less than a Hubble time, which means for small black holes, we have a process that can actually contribute relevantly for their massive growth. So at the moment, we are working on the model behind this code, and there are three main points that we can make better. The first one is loss cone model. There are two sides. First, theoretically, the loss cone theory was developed for tidal disruption events in a single component distribution of stars, and was later adapted to include extreme acceleration spirals and direct plunges. So there are still some open points in the last case, which is, for example, the fact that extreme acceleration spirals and direct plunges usually are produced by objects which are heavier than the average stellar mass then. So mass aggregation can play a role even in the distribution of angular momentum, which is usually neglected. And as Elisa mentioned today, the model for tidal disruption is either you have a full, either your orbit doesn't see the tidal disruption radius. Well, we know that partial disruption events happen, and so they might be included in the theory. Then, at the beginning of the system, we choose our two components, light and heavy objects, producing TDEs and black holes, but we don't evolve their potential. So you set it at the beginning, but it's not evolved self-consistently. According to 1D Fokker-Planck models, this will change the rate of about 20%, which is not a lot, and we think less than the impact of the first point. And finally, we would love to include a complete mass spectrum. But at the moment, already with two components, we are extremely slow. And for example, a work like the ones Elisa did with the 1D Fokker-Planck are still not doable with codes like ours. So I will talk you a bit about the first point, and in particular, how we are working on the model of partial disruptions. So how is the loss cone included in the theory right now? Okay, so now consider first a particle on this orbit, which is outside the capture radius. Current loss cone theory would say it doesn't know there is a loss cone, and the particle orbit will stay the same. However, it is possible that scattering events will drive your particle here on this sense, so it will move counterclockwise. So a particle is driven on a tighter orbit, and these tighter orbits, are very unlikely that you will receive another kick while you're in the orbit, so strong that they will take outside the loss cone again, meaning on an orbit whose pericenter is larger. So if you track in time the occupation fraction of an orbit, well, it will increase. You expect that to increase, and you have more particles approaching the pericenter, so arriving at the first pericenter passage, than those leaving, because you assume the particle will be destroyed there. Indeed, when you reach the pericenter, you can count what is the fraction of all of these particles that will end up in a tidal disruption event. However, we know that models say even particles outside the loss cone on these orbits will likely lose part of their mass, and this can affect their energy. So at the moment, we are looking exactly at that. Looking at results from hydrodynamical simulations, we can relate the pericenter passage in units of the tidal disruption radius with a mass loss, upper panel. And we can then translate it in a gain in energy or a loss in binding energy. So how much this mass loss, which is thought to be mostly radial, will move you outside from the inner regions, so on a loosely timed less tight orbit. And then, what are the effects of tidal excitation? So basically, you have a star, it gets strongly altered by tidal forces, so that the structure will start to oscillate, converting kinetic energy of the star, of orbital kinetic energy, into oscillations. So it will actually make your orbit more tight. So these are two competing effects, and what we are trying to do is what happens if you're doing events which strip very, very few mass, but you repeat them, because classical loss cone theory will tell you, classical relaxation theory will tell you relaxation will become inefficient at some point, so that repeated disruption are likely. So we track over time the mass loss at each passage, the energy loss or gain depending on the pericenter, and then see what happens. And so we identified three possible outcomes. It is possible that you will strip the mass, and at some point the remnant will have a positive energy, so it will be ejected from the system. Or it can happen that the sequence of repeated disruption will actually consume the star, so you will have a total disruption at some point. Or finally, that the star will finish all of these orbits and stay there. But what's the number of orbits we are considering? Well, the average number of orbits over which we think relaxation will act. So we take the average local relaxation kick, we translate it in a fraction of the orbit, like in a time, then we do the ratio with a period, and we translate it in a number of orbits that relaxation needs in order to act efficiently. And this is done with this parameter Q. Q is 1 over the average number of orbits that you can do before relaxation will take you away. So what we see is if you remember, objects will likely start at some point in that diagram of the eccentricity versus semi-major axis. At some point, they will start oscillating horizontally, which means they will mainly change their eccentricity or their pericenter. So what we see is that particles will be moved by relaxation from larger pericenter to the left of this panel, and at some point their energy will be changed relevantly. This is a relative change, even by 50%, just for moving, just for repeated partial disruptions. But this is something that it cannot be accounted for in current relaxation theory, because at the moment we have seen the theory says, well, initially you change your energy, but at some point you will only move in angular momentum. But we see here that over the same time scale, partial disruptions will change relevantly the energy of the orbit. So in making the story short, classical theories of lost cone are still on a question mark, are now on a question mark. Like, is it really true that the rate of particles we expect will end up in a total disruption or in a partial disruption? We don't know. Maybe they will be moved to less bound orbit, actually changing the true event, the energy of the true event we will see. So here is a summary of my plot, of my talk, and thank you very much.
Thank you, and as before, time for questions. Maybe I'll start this section. So we have studied ourselves a little bit of like, well, basically this tidal dissipation, basically circularization and in spiral due to like excitation of stars. So at least for like low mass, intermediate mass black holes, so at least for 1,000 solar masses or so on, we have seen that like actually less than 10% of the like accreted stars actually experience significant tidal effects. And this was because like most of the stars originate, accreted by the black hole originated from like bound subpopulation. So is this different for bigger black hole masses as you had in your studies?
Yes, in the plots I've shown you, we are considering a 4 times 10 to the 6 solar masses, so a Milky Way-like black hole. And that
Hi, Odelia, can you hear us? Perhaps you are muted. Bottom left, there is a symbol of a microphone. Can you see if it's on? We see your screen, but we don't hear your voice. So can you please check that you are not muted? I don't think I can. No, I can't. But she's sharing the. Can you use Chrome instead of Safari? Sometimes with Google Meet works better. Try to speak. Oh, wait. Okay, this was problem. Try now. But we should have heard anyway from the laptop. I can't hear anything from the laptop.
Possible to move to
coffee break, right?
Yeah, is it possible to move to contribution to tomorrow or something if this doesn't work today?
What time is it? Because now we have just a coffee break, you know.
Yes, yes. So we can start the break and have the. Because the coffee isn't there, so we cannot just switch.
I'm gonna go out and come back. 1 second. Perhaps it was our problem. Can you try to speak again? Oh, she's using a.
Yeah, but she didn't use them initially.
Initially.
So I think.
Oh, she's sending Zoom. Okay, let's try Zoom.
Yes.
direction perpendicular to the disk, and the gamma ray and X-ray emission of projected TDs are very close to GRBs. Actually, G1644, the first detected jetted TDs, was first believed to be a GRB. Here you can see the X-ray luminosity of 3 jetted TDs in colors launched in the direction perpendicular to the disk, and the gamma ray and X-ray emission of projected TDs are very close to GRBs. Actually, G1644, the first detected jetted TDs, was first believed to be a GRB. Here you can see the X-ray luminosity of 3 jetted TDs in colors launched in the direction perpendicular to the disk. And the gamma ray and X-ray emission of projected TDs are very close to GRBs. Actually, G1644, the first detected jetted TDs. I'm sorry, I'm hearing myself with like 2 different echoes.
Yes, we have some technical problems around here.
I'm sorry, Adelia. Our microphone was on, so maybe it was recorded and sent more times. Now, can you hear us correctly?
I'm sorry, I'm hearing myself with like 2 different echoes.
We have some technical problems around here.
Okay.
Could you check this?
I'm sorry, Adelia. Our microphone was on, so maybe it was recorded and sent more times. Now, can you hear us correctly?
Yes, I can hear you correctly.
Let's turn this on.
I don't know, where should I?
have seen before. Classic 10 EV disk, soft access, and then
that higher spinning black holes are the ones that are more luminous. I mean, the accretion disk around them is more luminous, so they're more easy to detect. But still, there is this trend, right, that the spin of the black hole goes down as the black hole mass increases. It has to do with either the black hole increases in mass from accretion or mergers, and how that will affect the spin. So the black hole mass then can also represent a different stage in the evolution of this black hole. So surely accretion depends on it, but I think it can have also secondary parameters that the black hole mass can represent in a galaxy.
So just to get if I understood correctly, because I'm very curious about this point. So your bottom line is basically that accretion itself is not intrinsically different as you vary the mass of the black hole. What changes are the properties of the gas that is being accreted as the central black hole changes its mass, and also perhaps its spin, how it evolves in time. That's bottom line.
It's a more complex interplay between the mass rather than it can represent other things just rather than how it goes in the equation. If we talk about the self-similarity of the solutions, surely you can scale away the mass and have something in gravitational radii and geometrized units and scale out the mass. So the problem is scale invariant in terms of the solutions. But then if the problem is astrophysical and depends on the question everyone tries to answer with their research, if you care about high redshift universe and what the metallicity might be playing, if we go with Eddington luminosity, that also changes regarding of what the material around is. You can have super Eddington mass accretion rate, but then the luminosity can be observed as below because you have photon trapping in the accretion disk. There are many, I don't think we can scale out black hole masses when we talk about astrophysical problems, but maybe the theoretical modeling of the accretion disk, then the black hole mass plays a different role. Probably I confused the problem then, but that's my understanding.
Yeah, just to add onto that, you know, the solution for the accretion disk can be self-similar. But yeah, changing the black hole mass then changes the Eddington ratio, which changes the Eddington ratio, which can change how the accretion proceeds for a given m dot, and changes things like the self-gravity radius. So like there was a paper a while back from Andrew King that showed once a black hole gets over a certain mass of like a few times 10 to the 10, you never expect to have a thin accretion disk anywhere that isn't self-gravitating. So that, the mass comes into it in that sense. But yeah, as you say, the solutions can all be scaled.
Just a comment about the last comment you made. That is definitely true. Just a comment. To my knowledge, the only model that managed to reproduce the trend, actually the data, the K-alpha line fitting of the spins at different masses, does only depend on accretion. And indeed, the masses of the systems for which the spins has been measured are not extremely high. It's a selection effect because you want to have a sufficiently high flux in the X-rays in order to model the K-alpha line. And so the effect of a sufficiently nearby in time measured merger is probably negligible in here. So accretion itself, even when it is similar, can explain that trend. As long as you were correctly making the point, you have you retain some information about the dynamics of the feeding process that could be different for different galaxies. And in that, I would agree with you. The point that you made about the fact that like you would observe less massive objects at higher redshift, my impression is that the observational selection effect goes the other way around. Like if you take this Loan data set, for example, and you search for systems that have 10 to the 6 lower masses, you are going to be limited to very low redshift. and systems that are not much chaotic and possibly being hosted in SC spirals, for example. While you need to increase the volume of the universe in order to start finding rarer objects like 10 to the 9 solar masses black hole, and then you are most probably biased at higher redshift, when the system could be more complex indeed.
Maybe we can move to the next point. Or okay, because I mean, so we sort of covered a bit the accretion process in different ways, and then I think something that came up very clearly from the talks that have been delivered today is the fact that in general also it's also came out right now, but the properties of the host environment can really influence how accretion, of course, proceeds on the massive black hole. So, for instance, something that I'm really curious about, and I mentioned already earlier, is the fact that, for instance, both changing look IGNs, tidal disruption events, and also those quasi-periodic eruption flares that have been recently observed appear to be triggered preferentially in those post-starburst galaxies. And this is something that, I wonder if we have any idea as of why this would happen, what could trigger it. Is it just observational bias somehow, even if I don't know how, can it be like that? And more in general also, I would be curious to know what you think about the fact that, the host environment can really affect the rates of tidal disruption events or extreme mass ratio in spirals that have been covered by Luca. So for instance, you need a very dense nucleus typically to have high rates of those events. And so, would it imply, for instance, post-starbursts are denser environment, or just that other environments that could be even more dense have some obscuration and we cannot observe those events in there? Maybe I said too many things. But, any idea as of why those post-starbursts seem to be so special in many different ways?
Yeah, I am also very interested. I'm also very interested in why that's happening. I do think some of it is concentration. Post-starbursts are generally more centrally concentrated than other galaxies at the same mass. And I think that makes sense for the TDEs and some of these other sort of accretion events, but I'm very curious about why changing look AGN also seem to have this dependence on being in quenching galaxies. And I wonder whether it's the quenching, I wonder whether it's central concentration, I wonder whether it's that these kinds of galaxies are more likely to be merger remnants. I don't know, I think there's a lot of things about post-starbursts that could cause these to be more prevalent, and I'm very curious about which one, or if it is just one of those things.
And also I was wondering, can we say anything about the stellar population which are in this environment, if those hot galaxies? Because I don't know, so I'm just asking question. Like we can simulate them somehow, yes, because there's some population synthesis, but I don't know if it was done or it's interesting to check.
So, because unless anyone has something to say, I don't want to monopolize. Okay. No, what is my impression is that, at least for tidal disruptions, what really matters in the event rate is the distribution of stars in your inner 0.1 parsecs. even, which is a scale that is basically unresolvable unless you look at the local group or something like that. So basically all those post-starburst systems are too far to really have a handle of what is their density in the relevant regions. So even if it is definitely true, I think it's kind of, well established that those systems are more dense in the center. It is unclear how much they are denser all the way down to the point at which you are interested in. So that's part of the problem in a way. Also, I think it's curious that TDEs and the changing look often happen in those kind of galaxies, which could, at least for some cases, hint towards the fact that they are related, and maybe TDEs are a manifestation of post-starburst are a manifestation of TDEs, but maybe it's not, probably it's not always the case.
So yeah, this is totally not my field, but I'm curious as to what can be found observationally, or if there are any proposals for the future.
So there is someone in Decker French's group. His name is Nicholas Earle. He's working on a paper right now about a TDE candidate. And part of what he's been trying to disentangle is the similarity between his models of TDEs happening in a pre-existing accretion disk and changing look AGN. So I do think that there is some interesting ties between the observational signatures of those two different things, and I wonder whether they might be related as well. I do think you'd have a hard time getting stellar population analysis of the central regions of these galaxies just because you have an AGN, at least in the changing looks, and you'd have too much contamination.
Well, since maybe this, I see maybe we don't have a lot too much, or maybe we want to think about this more later. Maybe we can move to the last point, which is the chicken or the egg, which was actually mentioned this morning, I think, in the presentation by Christian, if I'm not wrong. And so, the question is the black hole formed before or after the stellar population that surrounds it? So often, especially in the low mass and a nuclear star cluster, because if we listen to Christian's talk this morning, it looks like that, you cannot really form a nuclear star cluster if you have black hole accretion feedback. And so this, is a very, very interesting prediction to me. And the question is, do we have any other evidence, any other work, maybe also observational, that can help us understanding what came first, and what can we do observationally and also theoretically to understand this thing better? So what came first?
So at least my naive understanding is that the more natural path would be that the star cluster forms first, and then you have, if you have it, like the runaway stellar collapse, forming a black hole in the star cluster. But of course, this is unclear. But I would also like to add to what you said about my simulations, that this, of course, is not so clear whether this depends on the feedback implementation and the particular setting that is being looked at. So if you have feedback that is very directed, very collimated, then it might be that star formation around the black hole is possible, or if there's more cold inflows. So I would not claim that it's not possible to form a nuclear star cluster around IMBH. But it's more difficult, of course. Yeah.
And of course, like if the nuclear star cluster doesn't form the black hole at the first go, or like theoretically, well, also observationally, like nuclear star clusters have stellar generations of different ages, so basically star formation episodes also later. So this means that you form a new population of stars, you start the relaxation processes again, massive stars again migrate to the center, and you might have a later time like collapse scenario. So basically a nuclear star cluster might have multiple, well, the chicken might have multiple egg formation episodes, so to say. And of course, like if another black hole well falls in, we have heard about wandering black holes, minor mergers, major mergers. Like a major merger would destroy the nuclear star cluster completely, and we are at, well, at step 0 again. And of course, here in this case, with gravitational wave recoil, you might also get rid of the black hole. So both the nuclear star cluster and the black hole might be gone after a major merger.
So does it basically mean that we have very little way to tell apart those processes, or is there any maybe observational strategy we can think about to understand this better? Because I mean, from what Antti just said, it seemed like it is very complex, so it seemed hard to have a kind of an easy answer, right?
Basically, what I would like to know is the occupation fractions of black holes and nuclear, or these nucleation fractions, down to like dwarf galaxy scales. So that would maybe help to, I don't know, to improve the models we have for the formation of these objects.
If I can just add something though, for low mass galaxies, there's some work by Katja Farian and other people where they look at the metallicities and they look at the ages of nuclear star clusters, also the central region and then the rest of the galaxy. And for dwarf galaxies, it seems that the majority of nuclear star clusters, not all, but the majority of nuclear star clusters are globular clusters. So this is then like, we're not forming necessarily the black hole at the same time as the nuclear star cluster, because the nuclear star cluster was formed externally from the galaxy. Did the black hole form inside the globular cluster and then moved inside the galaxy with it? I don't know, like, if that's, you know, if we can find black holes in globular clusters. But like, that's another scenario that, you know, many of the nuclear star clusters are actually accreted globular clusters. So the formation mechanisms potentially of the black holes in the centers of galaxies, if they form there, and the globular clusters will be extremely different. They maybe have nothing to do with each other. And then I don't know whether there would then be a difference in the population of nucleated galaxies that their nuclear star cluster came from globular clusters. Maybe they don't host black holes, and maybe the ones that formed in situ do have black holes. I don't know, and I don't know of any observational ways to be able to tell the difference, but that's something to consider, that, you know, in situ nuclear star cluster formation and accreted globular cluster nuclear star clusters both happen. And they also, you know, you can accrete a globular cluster and then form another population of stars that was in situ, so then it's mixed. But I think these two scenarios are very, very different. So if you're doing observations of nuclear star clusters, I think it's probably very important to distinguish them, because I think the physical processes that went into producing them will be, like, very different. So yeah, I think that's something to be considered as well.
I guess this could relate to the entire galaxy more than nuclear star cluster, but like recent high redshift AGN see these overmassive black holes where the black hole to stellar mass ratio is much more higher at the high redshift compared to the local relation. So that would, I would expect that would mean that the black holes became massive first, then the star formed somehow after to make the local relation what it is now, to compare what's high redshift. So I guess that then we have to consider whether that stars at high redshift galaxies are formed at the nuclear star cluster first or around the outskirts of the galaxy first. But then, yeah, I guess at least for the SMBHs formed at high redshift, I would expect the stars to form later on. So maybe the nuclear star clusters could also have formed later on compared to where the black holes formed.
But for, is it on? Okay, yeah. For this specific aspect, I mean, I wonder, I don't know myself, I wonder how much observational biases can be actually at play to, I mean, give us this result. I mean, is it really intrinsic, or is there anything that just biases us towards finding black holes that are kind of overly massive compared to their hosts? Possibly not. I just wonder this because, I mean, I'm not an observer myself, so maybe someone knows this better.
Of course, I mean, from observational point of view, there is an observational effect. If you move to high redshift, until now, you preferentially selected the brightest ones, so you expect to be the most massive ones in the black hole mass parameter space. So you are preferentially picking the ones that are biased to high masses in black hole mass, and probably also they are the most luminous. So that's one thing to remember. And therefore it's not clear to me if and how these black hole scaling relations evolve at high redshift. I mean, it's not clear if the black hole really formed before the galaxy, because you are not completing your sample. You are missing all the low mass black holes.
We did well with discussion.
Yeah. Yes. So, I mean, if someone has some last point they want to raise, even if it is maybe unrelated to those specific things, but related to the talks of today, that's the moment. Okay.
I have a comment on the second question, because I think for the observed rate for the TDE, probably because we are just looking at the optical and X-ray band without any like infrared observations, because it reminded me of recent work. Someone performed the infrared survey and find TDE hidden in a dusty galaxy, and that galaxy is also a star formation galaxy, and it's a very nearby galaxy. So I think probably it's the discrepancy between the TDE prediction rate and the observed rates, because we missed a part of the wavelengths. And probably if we look at the other wavelengths, we could reconcile this discrepancy.
So, but this would mean that TDs, I mean, some TDs only emit in certain bands. Is it correct? That's what you are suggesting.
I don't know what's the real underlying mechanism of TDEs, but I know that there's observation they find power minus 503 power of in the infrared light curve, and they don't find any optical and X-ray observation about that source. So probably they have some intrinsic other wavelengths emission mechanism, but it's suppressed by the heavy dust, so we cannot observe.
Any comment or question on this? Or anything else?
Just one last quick question, because I mean, now we've mainly been talking about black holes in galactic nuclei, but is there a way to use TDEs to derive like constraints on occupation fractions or populations of wandering black holes and things like this? Do the TDE experts say there?
Well, I think this is a question we can, bounce back at you. Like, it's really the realm where n-body simulations should help us, because numbers are so low. Like, wandering black holes are usually surrounded by a small number of particles, and theory completely misses there, because close encounters play a role. The number is so low that even the idea of making a statistics on the evolution breaks down, because the number is low and you're no more predicting the evolution of a system. You're predicting the average distribution taken n copies of the same system. So really here the theory should count the number of particles, set a threshold, and say, here we go back to direct n-body simulations. Because it's extremely hard to imagine a wandering black hole and to estimate what would be the number and the properties and the outcome of an encounter with a star. So this is something we should really directly try to simulate and infer from that. It may take long, but it's definitely longer than the theory required for that.
Are there any observations of off-center TDEs? Is that something that people have found?
Kind of hard to localize within the galaxy, I'd say.
Okay, so you just know there is a TDE, but you don't know where in the system. Okay.
I think there are a couple of candidates. I think there is one in possibly in a globular cluster, but those are. I mean, you cannot be sure it's really a TDE. It could be a supernova. I don't know. So it's always hard to tell often, but yeah.
So if you talk also about failed tidal disruption event, I guess it's something similar to a peeling event, right? So the sources you would look for, it would be some hyperluminous X-ray sources, and there are really a few. The most famous, which is a well-known source, is called hyperluminous X-ray source 1 in the galaxy ISO 243-69. It's a work from the group of Natalie Webb. And this is an interesting source because for several years, with fairly regularity, he shined up to 10 to the 42 ergs per second, and then he shut down. Up to 10 to the 42, and then he shut down. And then recently, he started to delay this event by 1 year, then 2 years, and then it shut down completely, and then they interpret this as a failed tidal disruption event. This would be a source you theoretician might like to compare with, but there are, I only know like a few of these. Oh yes, and through X-rays, optical spectroscopy is confirmed to be in a cluster, so that triggers me, the thing you said.
Well, I think we are past 5, so maybe it's time to stop. Thank you so much for participating in the discussion. And do we have any announcement? No? Let's go drinking and see each other tomorrow morning. Yeah.
If any of you would like to know anything about where to hang out in Palermo,